And I assume that everybody has attended my session last Saturday, 30th of January 2021. And that was the opening session, and we had a great discussion. And what we discussed was we talked about number systems. We discussed about what are different types of number systems. Mainly, we talked about decimal number system, binary number system, octal number system, and hexadecimal number system. So, four types we have identified. Very important discussion we did last Saturday. And that discussion was how we can move between two number systems. Because if you remember, I said human use decimal number system and some fantastic reasons I shared with you why human use decimal number system. If you remember, I said that human has 10 fingers. So naturally, human can count 10 digits. So the number system is base 10, that is decimal. Machine use binary number system, that is 0 and 1s, called bits. And all different conversions we discussed in the last session. 12 conversions I taught you, if you remember. And some practice questions also I have given you. I assume that that homework is complete and you do not have major queries about that homework. A lot of questions are given to solve or to practice as homework. I also assume that all the concepts you must have studied, you must have reviewed and ready for lecture session 2. As usual, let's start our session with a common practice. I will say my common practice, and that practice is time to test, just to see how much you have studied, how much you know about our previous discussions. And for that, here are some questions, and those questions I will put all together one by one. And I expect that you should be answerable to those questions. So let's check what are the questions. What is a number system? What are common number systems? I think this answer I already gave. What is a binary number system? What is the value of 11111111 binary in hexadecimal? I will wait here for some time just to check your responses. And you can either unmute and you can answer, or you can also use the chat box to answer these questions. So let me see how you are answering. Yeah, it's your turn. I'm looking at the chat box. Anybody who will answer these questions? Like I said, you can unmute and you can answer, or you can also use the chat box. Choice is yours, but answers are expected. Yeah, that is right. The answer to the last question is FS. That is right. No, that is not FS. I was just checking how many of you do the copy paste and say FS, FS. So the answer to last question is not FF. Yes, what is your opinion? I have given you both options, FF as well as not FF.
Sir, मैं just अभी join हुआ, कुछ important पूछा आपने किया?
No, I'm just asking some questions. What you see on the screen.
Okay.
Those questions we are just discussing. I'm waiting for some answers.
Okay.
Okay, answer FF is correct. Let's not go into more complexity. So answer FF is correct. Agreed. I was a little keen to know how this FF is coming. That is the reason I was going into that. But anyway, FF is correct. Carry on with the remaining 3 questions. I think people are answering from last to first. So let's call it as V4. Anybody who can answer remaining 3 questions? Question 3, 2, and 1. What is the binary number system? What are the common number systems? And what is a number system? Anyway, I think people are still thinking what are the answers to this question. Anyway, I'll just continue. Now let's see what's there in lecture session 2. What is today's agenda for our session? Now today we are going to start with discussion of digital circuits. Last time, if you have attended, little bit of discussion we have started. I talked about 10 minutes, I think, or maybe 15 minutes, and that discussion we will be taking further. We will discuss logic gates. We will discuss about Boolean expression. We will discuss about basic circuits like ideal circuit and a concept called K-map. We also plan to have discussion about decoder and multiplexers and sequential circuits. So a lot of points are there on my agenda. Let us see how we can manage in the given time. In case if we could not, then some concepts slightly may roll over to the next discussion. But we will try to complete as per our agenda points. And these are the references that I will suggest for today's session. I will suggest a reference. It's basically a textbook or even an ebook by S. Rao, Digital Computing, Digital Logic, and Digital Design, Silicon Technology. This is not listed in your syllabus, but this is one of the good reference. And second reference is a textbook, which I will definitely recommend, and it is listed in your syllabus, is Modern Digital Electronics by R.T. Jain. So these are 2 references for our today's discussion, and you can also refer it further. No doubt all the material and all that will be getting, but standard references are also important, so I just refer it. Anyway, now all is well, and we are ready to go ahead. Our quick review is complete. If you are ready, please type YES in the chat box. Okay, I can see some answers, and I think the answers are okay. Okay, excellent. I think everybody is ready, and let's go on. Now let's start with the discussion of digital logic circuit. One gentle reminder before I go ahead, so that this confusion will not come. And this reminder I will put at the start of every session. You will get the notes of all these modules in the form of ebook, maybe in next 1 or 2 days. That will be available. Module 1 notes are ready in ebook, and you will be able to access it in 1 or 2 days. I'm also sharing PPT in PDF format, like last Saturday, whatever I taught. All those PPTs I have already shared in PDF format in the office, and they will make you available. Today's session also, all PPTs in PDF I will share. So all this material will be given to you. I'll try to keep dictation as low as possible, because in online teaching learning process, we have to more focus on understanding, because we'll be using a lot of tools like my PPTs are animated. There are a lot of graphics on my PPT, and in any way I'll be sharing, these videos are also getting recorded. So all these materials are available to you. What is more important is understanding. In classroom, normally the methodology is different, and that is the reason we try to keep our own material. So what I suggest you is that if you feel any point important, you can note it down. You can have a notebook with you, and if you feel that any PPT is important, you can take a pic of it. Everything I'll be sharing, but if you want for immediate reference, then you can use it. Okay. Anyway, let's go ahead and let's start with digital logic circuit. Now the question is that, referring to our last session, we know that when we talk about computer, when I talk about any system which is based on computer, it is basically a system which works on binary number system called bits, and there are 2 symbols, 0 and 1, called as binary digit. So the question is that how we are going to process this binary digits or bits. What is the method? What is the facilities. For that, we need special circuits which are called digital logic circuits. So essentially, all the processing of zeros and ones, or I can say bits, we always do using digital logic circuit. So in the last session, we understood if my data is in decimal or in a human readable form, then how we get that data in binary. Of course, we discussed it for numbers because whatever discussion we did, all conversions that we did, they're all based on numbers. That is because that is what is required as a part of our studies. And we know if my data is in decimal, if I talk value like 1, 2, 3, 4, then how I get it into zeros and ones. Now that work is done. Now the next question is that how I'm going to process those zeros and ones. Like I want to add zeros and ones, or I want to compare zeros and ones, or I want to multiply zeros and ones, or I can say bits. Then we use digital logic circuit. And these circuits are used to process bits, zeros and ones, and we perform lots of operations on those particular bits. Like I said, one operation is addition. Now my question is that why we prefer such digital systems? What is the reason? Can you tell me what is your thought? Why we are studying about digital logic circuits? Why we prefer digital system? What is the reason? Anybody who can share their
The
thought?
computer can compute only in that form.
Okay, because computer works with zeros and ones. Okay, any other answer? Anybody? Why we prefer digital system? What is the reason that everywhere nowadays we find that systems are digital systems. Our communication is also digital. Your television reception, your telephone communication, your mobile communication is a digital system basically. Anyway, there are many reasons because that is not our focus of discussion. But before we go ahead, I feel at least you should know why we talk digital systems, why we design digital system. One of the reasons why we prefer digital system is because opposite of digital system is called as analog system, ANALOG. Some years before, many systems were analog systems. They used to process analog signal. I hope you are aware what is analog signal and what is digital signal because it's a very elementary level. The signal which is discrete, like 0 or 1, that is basically digital. And a signal which is continuous, like sine wave, that type of signal is called as analog signal. So one of the reasons why we prefer digital system is these systems are more immune to the noise. Noise means all the unwanted disturbances that we get when we do communication or when we design a system. That noise problem is more in analog system and is comparatively less in digital system. This is one of the big reasons. Specifically in communication applications, this is the reason why most of the communication applications are digitized because the effect of noise is very less in case of digital, but it is much more in case of analog. And of course there are many reasons, but a couple of reasons I want and I should talk and we'll go ahead. Second reason is that nowadays everything is based on software. When I teach subjects like microprocessor or computer organization, what we're talking, or programming languages, I always say that it's the hardware which does the job, and software tells hardware how to do the job. And I always raise one question: how we get that software? That software we get through a program. It is a very simple link. So my point is that digital systems are more close to the programming and software, and analog systems are slightly away from programming and software. So integration becomes difficult. If you want to integrate your software with your system, and if the system is digital, it is comparatively easy. But if the system is analog, then it is comparatively difficult. So there are some reasons, and we go for digital system. Now, these digital systems are classified into types. One is called combinational systems, and second one is called sequential systems. If you remember, I was talking about it last Saturday, and we are starting with that. So it's a continuous discussion. Now, what is a combinational circuit, or what is a combinational digital system, to be more precise? If you see carefully, it's a system such that my output depends on present state of input. Okay, you will understand as we go ahead with more and more details, because this is something where it all starts. Our story starts at this point. So point is, if you apply some input, 0, 1, 0, 1, and if you generate some output, then this output depends on present state of input. Such digital systems are called combinational systems. Observe it. Let me use a pen. Okay, let me highlight this word. The word is combinational system. Okay, and just give me a couple of seconds. I will go for better color. Okay, so combinational systems. And second one is called sequential system. Now, what is a sequential system? Sequential system output depends on present input as well as on the previous input. See this carefully. Okay, and now if you see carefully the diagram on the block representation, you will find that there is a feedback which is coming from output to input. Now, this particular feedback represents previous input because previous input refers to whatever result you have generated. And to store that, we need a memory here. So such systems have a concept called memory. Because the question is how we get this particular previous input. See the word previous. Previous refers to history. And history means there has to be some facility. That facility is called as memory, to remember. So these systems have memory, and these systems, combinational systems, do not have a memory. See that. Possibility is less, but because we are starting the discussion of digital circuits, this can be a question: differentiate between combinational circuit and sequential circuit. Okay. In those notes, everything is given. Again, a gentle reminder. And all these points you will find that output depends on present input. That is combinational. Output depends on present as well as past input. That is sequential. There is no memory in combinational. We always need a memory in sequential because already the word is highlighted. Previous means history. Means I have to remember. Means I need a memory. Anyway, like I said, as we go, this concept will be more and more clear, but probably this is where it starts. Now let me give you one example so you can visualize what exactly is a combinational system and what is a sequential system. Okay, we will not take technical example, we will take some general example. Okay, our academy as an example because we have to learn many concepts. So we will take general example just to have an analogy. Example is that you are in semester 4 and you will appear for examination and you will get some result. And that result depends on your current efforts on different subjects, whatever studies you are doing, whatever I exams you are doing, or whatever marks you are getting. So this is like for a current semester, your present input will decide the output. So it's like a combinational system. But when you pass out as a B, maybe after next 2 years, and when your final result will come, okay, maybe nowadays the system will be different. But when we graduated, our final result was the average of semesters. So it was the performance of semesters like 5, 6, 7, 8. So there, I have to refer to all my performances in the previous semester. So that is like a sequential circuit. So combinational circuits are little specific, I can say at the moment, and sequential circuits are little general. And one more thing you will observe in the definition if you are alert. When I say in sequential circuit, output depends on present input. That means it includes combinational circuit. Because see, these phrases are same if you observe carefully. See, output depends on present state of the input, and here also same phrase is there. Output depends on present state of the input. So I have clearly highlighted this common factor. That means sequential circuit includes combinational circuit. You cannot design a sequential circuit without combinational circuit. There can be a good oral practical or I can say interview question. Can you design sequential circuit without combinational circuit? If you say yes, that means you don't know anything. Because combinational circuits are included in sequential circuit. That's why those definitions, if you read carefully, they are very interesting because everything in combinational is there in sequential. And that is the reason we will study combinational logic circuit. In your syllabus also, if you see, more focus is on combinational logic circuit and less focus is on sequential logic circuit. Your syllabus is huge. Let us be very clear. Last time also I said that for me and you it's a big challenge that how we are going to go through such a huge syllabus. But anyway, we are doing good as far as our sessions are concerned. Let's go ahead. Now that point is clear. What is combinational and what is sequential. So let's start with one type of combinational circuit which is called logic gates. Now let me talk through some practical examples before I bring logic gates. Okay, so that you will understand better. If you recollect so many subjects you have studied and you also have studied BEE and in that you may have studied some part of semiconductors. My point is that to build any circuit, you always need some components like resistor, capacitor, inductor, transistor, diode. This is something which is the minimum requirement. Okay, so like that, when we talk about digital circuit, what we need is a combinational circuit called logic gates. What you see, the title of my slide. Okay, and what are logic gates? Let's understand. Let's bring it. You can see the first gate is called as AND gate. Second gate is called as OR gate. Third gate is called as buffer. This is normally not counted as a gate, but I don't want to skip it. That is the reason I have added many references. They don't count buffer as a gate. Fourth is NOT gate. Okay, so there are total 3 logic gates. Let us not count buffer, though we will be studying. But you will see one saying buffer is not a logic gate. And OR and NOT, these 3 circuits, these 3 combinational circuit are called logic gates. Okay. Now the question is that means what? Because and or not these words we got familiar and there are some expressions visible. Okay, we'll talk about it. But the question is that how they work. Like if I take a resistor, then it works with the Ohm's law, or if I take diode, then it works with a simple PN junction, that is majority carriers. And every component has its own working. So what is the working of this particular logic gate? That is the question. Because okay, agree that there are 3 gates and or and not. That working we understand through truth table. Observe it carefully. This particular table is called as truth table. TRUTH-TABLE. Okay. Now what is the truth table? Truth table means we provide all inputs and we show one output or many output depending on what we are talking. Okay. Now if you see very carefully, you will find we represent AND gate using a symbol which is visible. Okay. This is a symbol for AND gate. There is no specific name. So this symbol is AND gate. And AND gate has 2 inputs. You can see X and Y. And it has one output which is called Z. And how this particular gate works? This particular gate works according to a truth table where X is one input, Y is second input, and Z is the output. And a very simple truth table if we read. When both inputs are 1, then my output is 1. I repeat. When both inputs are 1, then my output is 1. You can see. And when any of this particular input is 0, you can see this is 0, this is also 0. One of the input is 0, one of the input is 0. So when one of the input is 0 or both inputs are 0, my output is 0. You can see. So this combination of input and corresponding output is called truth table. And we always represent logic gates using a truth table. You have to remember all this because this is all fundamental. Okay, and because our examination pattern is slightly different, you may get a question, there's some symbol will be given to you, and the question is identify the following gate, and such symbol will be given, and you have to identify that out of so many options, the right option is AND gate. So there it starts basically. Okay. Now the question is, what is the meaning of 0 and 1? Can you tell me what is the meaning of 0 and 1? Anyway, there are total 20 students in our team. So can you tell me what is the meaning of 0 and 1? What do you see here? Anyway, you can answer, or you can also use the chat box.
0 means there is electrical signal. No, there is not electrical signal, and 1 means there was an electrical signal. Okay, I guess.
Yes.
0 is off and 1 is on.
Okay, 0 is off and 1 is on. That is right. Anybody else? Yes, you're most welcome because you have to participate, and we are not doing studies of 10th or 12th. We are doing a complex professional studies, so your participation is very important. Anyway, now let me explain what is 0 and 1. Basically, 0 and 1, these are voltages. Understand? So if I write, in fact, if I draw a simple waveform, then you will better understand what is 0 and 1. Suppose this is a simple square wave. Okay. This is a simple square wave, and this particular voltage is +5. Okay, and this particular voltage is 0. Okay, we always measure voltages in volts. Okay. This voltage is 0 volts and this voltage is +5 volt. Then basically what is 0 and 1? 0 means a very small voltage. Okay, maybe between 0 to 1. See, this range is called as logic 0. 0 volt to 1 volt. That is called as logic 0. And any voltage from 4 to 5 volts, okay, 4 to 5 volt is called as logic 1. So normally logic 1 is high voltage, ideally +5, and logic 0 is a low voltage, ideally 0 volt. So basically when you talk bits, you talk voltage, please remember. Okay, when you talk bits, what you talk is a small voltage, either slightly high voltage like +5, which is a big one, and a low voltage, ideally 0, that is big 0, but practically there is a range. Okay, we do not talk specific value, we always talk about range of value. Okay, so if my voltage is 4, then it is logic 1. If my voltage is 4.2, it is logic 1. If my voltage is 4.8, it is logic 1. If my voltage is 2.5, then it is neither 0, neither 1. Okay, that we will not discuss now because that is a totally different story. We will only talk about 0 and 1. Anyway, so one gate is called as AND gate. And this is how we represent AND gate. We represent AND gate using a small dot. Observe it. X and Y. That is how we read it. X and Y. That is how we read it. Okay, or X dot Y. That is what is AND gate. Second gate is called as OR gate. And now you will see that this gate also has some symbol. There are 2 inputs, X and Y. There is one output, that is Z. Okay, there is no need to write X, Y, Z. You can write ABC also. Okay, you can also write ABC to represent different input and output combination. Or you can write PQR also. But normally we prefer to write X, Y, Z. So X and Y are the input and Z is the output. Now if you compare AND gate and OR gate, you will find that there is a difference. Now what is the difference? Difference is that when one of the input is 1 or both the inputs are 1, result is 1. I'm talking OR gate. See, one of the input is 1 or both the inputs are 1, result is 1. And when my result is 0, my result is 0 only when both the inputs are 0. This is the characteristic of OR gate. Okay. Third gate is called as NOT gate. Third gate is called NOT gate. Now what is a NOT gate? NOT gate is also called inverter. Okay, I will talk about this later. Before I will talk at the end. NOT gate is also called inverter. Now what is the characteristic of NOT gate? If you see carefully, it has only single input and it has a single output. See carefully. And symbol is slightly similar to diode because in diode if you recollect, we have a vertical line here and there is no bubble here. Okay, and it's very interesting if you see the truth table because what we say, if my input is logic 0, my output becomes 1, and if my input is logic 1, then output becomes 0. This operation is normally called complement. COMPLEMENT, complement. So if you want to change 0 to 1 or if you want to change 1 to 0, then for that we use a gate which is called a NOT gate. Okay, and is represented by bar. Observe that X bar. That is the meaning of NOT gate. Finally, if you see buffer, because this is not a gate, but what is a buffer? Buffer is a small circuit which will allow input to pass to the output. Observe it. So if you see the truth table, you will find if my input is 0, then my output is 0. If my input is 1, then my output is 1. Okay. Here we will not talk when we use buffer because this will be too early to start talking about design and applications. But we will remember all these particular gates except buffer in the form of truth table. Okay. Now let's go ahead. These are total 3 gates, and or and not. Buffer is just a supplementary circuit called combinational circuit. Buffer is not a gate. Again, I am repeating. Okay. Now there are some more gates. Next gate is called as NAND gate, which looks like this. Observe it. NAND, NOR, and XOR. These are the further three gates. Okay. Now let's start. NAND stands for not and. That is the full form of NAND. Not of and. That is called as NAND. Okay. And that is the reason, if you see carefully, this is my AND gate. Previously we were talking about AND gate. And in that AND gate there is a bubble, because this bubble we use. This is normally called as a bubble. This circle is called as a bubble. BUBBLE. So this bubble we have seen in NOT gate. See this. See, this is a characteristic of NOT gate. And this we are putting here. Okay. And such gate is called as NAND gate. Now what is a NAND gate? It is opposite of AND gate, because if you compare truth table of AND gate again, see. Okay. My input is 1. Second input is also 1. Then only my result is 1. Otherwise my result is 0. This is the characteristic of AND gate. Okay. So when my output is 1, my output is 1. Then both inputs are 1. Now in case of NAND, you will find this is something different. Observe it. It is exactly opposite. That's why it is not of AND. And I told you, not complement. Complement means opposite. Okay. So you can see it is exactly opposite of AND gate. In case of AND, 0 0 is 0. So here it is 1. In case of AND, 0 1 is 0. So it is 1. Not of AND. In case of AND, 1 0 is 0. So it is 1. In case of AND, 1 1 is 1. So it is 0. Because not of AND. That is called NAND gate. NOR gate is called not of OR. Okay. So you can see AND and NAND, they are complemented. NOR and OR, they are complemented. Not of OR is called as NOR. And now if you see the truth table of OR gate, let's go there once again. Okay, so this is the truth table of OR gate. We have identified that my output is 1 when both inputs are 1, or any input is 1. Okay, and only when both inputs are 0, my output is 0. Now this becomes opposite in case of NOR. See, in case of OR, I'm taking OR as a reference. 0 0 is 0. Not of 0 is 1. That's why it is NOR. In case of OR, 0 1 is 1. Not of 1 is 0. In case of OR, 1 0 is 1. Not of 1 is 0. In case of OR, 1 1 is 1. Not of 1 is 0. Okay, just give me 1 sec. My phone is ringing consistently. I'll be back in 1 minute. Okay? Just give me that question. I'm extremely sorry because that phone was consistently ringing, so I thought I should stop it. That is the reason. Anyway, so coming back, I was talking about NOR gate, and I said not of OR is called as NOR, and we have mapped it how it is not of OR. Now the last gate is called as XOR gate. You can see. Now this XOR gate is slightly different. Okay, XOR gate do not have any counterpart. Now if you are very alert for last half an hour plus, you will agree that we have a very clear understanding of these logic gates. We have AND gate, we have OR gate, and we have NOT gate. These are the three gates. They are called basic gates. BASIC. Okay. AND gate with NOT gate is called as NAND gate. OR gate with NOT gate is called as NOR gate. Okay, so they are complementary. And NAND or NOR. Okay. XOR gate is a gate which is slightly different. You can see what is the symbol. Okay. This is a symbol of XOR gate, and you can see the symbol of XOR gate is similar to OR gate. Only we have a parallel line. Okay, and same truth table is visible with one difference. If you compare 0 0 is 0 in case of OR, 0 1 is 1 in case of OR, 1 0 is 1 in case of OR. So this is similar to OR. Okay, and 1 1 is 1 in case of OR, but here it is 0. See this. Okay, so this is the only difference between XOR gate and OR gate. If I highlight it, this is the only difference between XOR gate and OR gate. Okay, now let's understand how these gates are useful. Okay, because now we have brought all the gates in our discussion. Now let's understand how these gates are useful. But before I go for it, if you have any specific query, then you can raise your query, because we are discussing for almost 45 minutes. Check it out.
XNOR gate is a question.
There is a XNOR gate, but XNOR gate is not very common as far as design is concerned. That is the reason I did not refer it. So what we are calling XNOR is existing. There is existence of XNOR. But if you take applications, then you will find that it's not so much used in the design of application. That is the reason I did not refer. But it's there. Your query is valid. It's there.
Okay, sir.
Yeah. Any other question? Check it out. Okay. If you do not have any questions, please type YES so that I will understand. Everybody is alert and we can move ahead. Yeah, that's great. Anyway, now pay attention. Let's go ahead. That is great. The point is, understanding is, we have identified total 5 gates. What are the 5 gates? 5 or 6? Let's count. AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate. Total 6 gates. Okay, and like one query was asked, let me clarify to everybody that there is opposite of XOR, which is called XNOR. Okay, XNOR, XNOR. But that gate is not very common as far as the design is concerned. That is the reason I did not refer. But since there was a query, let me talk 2 minutes. Now what is XNOR? XNOR is a complement of XOR. So we have basically pairs, if you want to visualize. And NAND, they are complement. Or NOT, they are complement. XOR, XNOR, they are complement. So in XNOR, 0 0 will be 1, 1 1 will be 1, 0 1 will be 0, and 1 0 will be 0. So in rare case, if somebody asks what is XNOR, then you should know. That's why this particular point I'm just clearing. So total 6 gates are there, which are commonly used. And 7th one is called as a buffer, which is not a gate. Okay, it is just simple circuit which will take input and it will pass it to the output. This is also required at many places. Now let's understand how these gates are useful, and then we give a thought, something more, something new we will study. Okay. Let's take the last gate, which is called as XOR gate, because probably that can be the good place where we can map the application. Pay attention. Logic gates, we are going to complete, and we are going one step further. I already said all these circuits, like logic gates, we use to process bits 0 and 1. Because if you see the truth table, you will find it is in terms of 0 and 1. And we always talk in terms of 0 and 1 that 0 0 is 0 like that. Suppose you want to compare 2 bits. Okay, how we compare numbers in decimal? 10 20. We say 10 is greater than, less than, not equal to 20. These are the possibilities. 10 is less than 20 like that. So if you want to compare 2 bits, okay, suppose there are 2 inputs and those 2 inputs are 2 bits, and if you want to compare, then we use XOR gate. XOR gate we normally use for comparison. See how? If you see the truth table of XOR gate, you will find that when both bits are equal, observe it, 0 0 and 1 1, result is 0, see. And then both bits are not equal, the result is 1, see carefully. So what I can do, see this interesting, what I can do is, I will apply one of the input as x, I will apply one of other input as y, and I will see what is z. Okay, if my z is 0, that means both the inputs are equal. And if my z is 1, that means both the inputs are not equal. So one gate will compare two bits. And such questions are possible in your examination because when I teach, I always use one statement. Smart people ask smart questions, and one good question can be, which gate you will use to compare two bits? AND gate, OR gate, NOT gate, XOR gate. And you should be able to identify the right answer is XOR gate. Okay, that's why this truth table is important because this truth table is used to indicate working of all these logic gates. Okay, anyway, same I can talk with AND gate. Everywhere I will not talk because we have to go ahead, but I can also talk at the AND gate. See, suppose you want to multiply two bits. Okay, you want to multiply two bits. Then I will use AND gate. Observe it. 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 1 into y is 1. So if I want to do multiplication of two bits, then I will apply bit 1 as x, I will apply bit 2 as y, and I will observe z, which is output, and I will get the corresponding output just by the characteristic of AND gate. So these are the very simple applications you can directly map when we start studying of logic gates. Last few comments and our discussion will be complete and we will go one step further. Now you have to be very alert because there are some words that I am going to introduce. Can you see certain statement like x dot y, x plus y, x bar, bar stands for complement, okay, or x dot y complement. There is that not of AND. What is AND? X dot y, and what is not complement? Okay, so x dot y bar, what is or x plus y, and what is not complement? So x plus y complement, and this is different. This is XOR. This is a symbol of XOR. Okay, these statements are called Boolean expression. B-O-O-L-E-A-N. Boolean expression. E-X-P-R-E-S-S-I-O-N. Okay, now what is a Boolean expression? Let me introduce you because we will require it in further discussion. Boolean expression is a statement which will indicate working of some logic circuit. So you represent working of your logic circuit, digital logic circuit, using Boolean expression. I repeat once again, you represent working of digital logic circuit using Boolean expression. Boole is the name of the scientist who has designed some rules called as Boolean algebra. Okay, I repeat, Boole is the name of the scientist who has designed certain rules called Boolean algebra. Those rules we will see in coming slides, and such expressions are called Boolean expression. So this is a Boolean expression. This is also Boolean expression. This is also Boolean expression. All these expressions also you have to remember because these are all basic gates. Okay, you cannot design a circuit without resistor, diode, transistor. Similarly, you cannot design a digital circuit without logic gates. It's that way. Okay, now let's go ahead. Now the question is, let's see how we use all these particular logic gates for implementing a digital hardware. Okay, let's understand it. This is a little simple. I told what is a Boolean expression. Boolean expression means working of some logic circuit or working of some digital circuit. Okay, this is the working of NAND gate. This is the working of NOR gate. That way. Okay, let's take some Boolean expression. Okay, this is a Boolean expression. Observe it. This is a random Boolean expression. Okay, we are not bothered how it is calculated, how it is received, or what is the methodology it is created. We will study it now. Suppose this is my Boolean expression. What is the Boolean expression? Once again, Boolean expression is a statement which will indicate working of a digital system in terms of input and output. What you see on the right hand side are all inputs, and what you see on the left hand side is output. So this is my output, and this is my input. Observe it. These are all my inputs. These are all my inputs. These are all my inputs. Because there is a truth table. That is the reason I have not written. But I write z is equal to x dot y complement. Z is equal to x plus y complement. Z is equal to x XOR y. Okay, so my LHS is basically z. But we talk in truth table. That is the reason that complete expression we have not written. My point is, suppose this is a Boolean expression. Let's assume that this is a Boolean expression. Then how you are going to implement it in digital hardware? For that, we use logic gates. Observe it how. Okay, just observe. I'm silent because I just want that you should try to map before I go. If you are alert, you will be able to do it immediately and very quickly. Observe it. This is A complement. How I will get A complement? I will get A complement using a NOT gate. Okay, so you can see I'm using a NOT gate. And to this NOT gate, I'm applying input A, C. So here I will get A complement. Second is B complement. How I will get B complement? For that, I'm getting another NOT gate, C. So if I apply input as B, my output will be B bar. Now if you see it is a dot. Dot means it is AND gate. That is the reason both these I'm applying as input to AND gate. See carefully. Okay. Now if you see inside parenthesis, then there is C plus B, and this plus indicate OR gate. That's why I'm using here OR gate. See this. And my input is C and D. So here I will get C plus B. And this C plus D is again ANDed. That's why I'm applying as input to AND gate, and my result is Z. And this is the hardware for this particular Boolean expression. Okay, so maybe in your examination, you get some expression like this, and you should be able to draw hardware using logic gate. Even that skills you should be able to develop after this discussion is complete. Of course, at basic level, nobody will give you huge expression because it will take more time. But at least you should be able to think what are the inputs for every input, which gate I should use, and how I should connect the gates. That ability you should be able to develop. This I can do in one more way. Observe it. And both are correct. Nothing wrong in that. See. So here what I'm doing, I'm taking this NOT gate. I'm taking this second NOT gate. Okay, and instead of using single AND gate, I'm using two AND gate. Observe it. Okay, so this is the input A becoming A complement, which is given to this particular AND gate. This is input B, which becomes B complement, which is given to this AND gate. And it is multiplied with C plus D. So essentially, I'm calculating this particular part, and then I'm ANDing with this particular part. So I'm doing in two levels. This is level 1, and this is level 2. Okay, so this particular level is AND gate 2, and this particular level is AND gate 1. See, even that is possible. Okay, don't be under the wrong impression that your logic gates are always the 2 input. No, your logic gate are minimum 2 input. If you take AND or NAND NOR XOR XNOR, if you want to add, these are the gates which require minimum 2 input, and NOT gate requires only 1 input. But your gates may have more than 2 input. Like this AND gate has 3 input. Such gates are also available. 3 input AND gate, 4 input AND gate. Okay, so what is available is 2 input gates are available, 3 input gates are available, 4 input gates are available. But NOT gate is exceptional because NOT gate always have 1 input and it always gives you 1 output. Rest all the gates you can have different flavors. 2 input AND gate, 3 input AND gate, 4 input AND gate. This all is available as a standard hardware. Just like we visit our Silicon Valley, that is Lamington Road, and we purchase resistor, we purchase capacitor, we purchase diode. Like that, we can go and we can buy 2 input AND gate, 3 input AND gate, 4 input AND gate. ICs are available. Standard ICs are available. Okay, so all these gates are available in the form of IC, integrated circuit. You may have seen integrated circuit in the labs in your previous studies of engineering. Anyway, so I just taught you how we convert Boolean expression into the hardware. Okay, if you have any query, then you are free to ask. Check it out. We have completed around 1 plus hour of discussion. Check. I'm waiting for your query. If at all you have any query, then go ahead and get it clear.
सर मैथ्स में जो हमने लॉजिक पढ़ा है और ये जो लॉजिक है कुछ खास मेजर डिफरेंस है?
नहीं, मेजर डिफरेंस नहीं है. आपने बूलियन अलजेब्रा पढ़ा है मैथ्स में?
यस सर 11 12 में पढ़ा.
Very nice. So listen, there is no major difference.
यस सर.
I can't hear you. Your voice is very low.
For this particular expression, I have to
For this particular expression?
I mean, when I was solving Boolean expression, this was become calculus, right?
See, here I'm not solving Boolean expression. Okay, I'm implementing Boolean expression. I have not taught you how to solve Boolean expression. That I'll be talking. Okay, so what I've done is the implementation of my Boolean expression. Okay, before solving, I taught you how to implement it, and that implementation you can do either from left to right. I will recommend that if you do from left to right, like if you recollect, I started with a bar, then I went to b bar, then I generated a bar dot b bar, then I talked about c plus d and I joined it with and that is a bar dot b bar output. So that way we normally realize the Boolean expression. So if you go from left to right while implementing, it is a better option and it is a better practice. That is the answer. Okay, there is one question in chat box. How many maximum input can we have for the gates? Gates can have maximum 8 inputs also. So you have wide range of gates available. But normally you will get 8 input and gate or 8 input or gate. Even those gates are available. Are there any efficiency difference between these two? Which one is majorly considered? See, there is no question of efficiency, but I will tell you what is the thought process. Thought process is that if you compare these two diagrams, then you will find that here your wiring increases basically, and your number of components also increases because here you are using 4 gates, 1, 2, 3, 4, and here you are using 5 gates, 1, 2, 3, 4, 5. Okay, so the difference is that if you increase the wiring and if you increase the component, then the reliability decreases because component have a life. Human has a life, even component has a life. Okay, so if you use more number of components, there is a more possibility that some component will fail and your circuit may not be so much reliable. So we should not just go on adding the component just because I am finding it easy. No, you should try to minimize the component. So I will say that this particular design is a better design and this design is correct for second, but I will not prefer it. That is the answer to your question, and that is how it is different. And I want that you should know. That is the reason I have shown both. Okay, can we go ahead? Okay, let's go ahead. If you are ready, please type YTS so that we'll go ahead and we'll continue the next part. I want some good YTS. Excellent. Nice, very nice. Okay, now focus, alert. Let's go ahead. I taught you 3 different aspects. Okay, I taught you what are the types of digital circuits. I can say differentiate, combinational and sequential. I taught you what are basic logic gates. Symbol I introduced, truth table I introduced, Boolean expression I introduced. I taught you how to implement Boolean expression, some random Boolean expression we have taken, what you see on PPT, and we have implemented it in a digital hardware. Okay, now let's go ahead and let's see how we make this Boolean expression. क्योंकि अगर आपने थोड़ा कॉमन सेंस किया तो यू विल एग्री कि मेरा जो फाइनल डिजिटल डिजाइन है वो डिपेंड करता है Boolean expression पे. मेरा Boolean expression जो है उसको मैं रियलाइज करता हूं. सी इंप्लीमेंटेशन ऑफ डिजिटल हार्डवेयर मेरा टाइटल है. मैं इंप्लीमेंट कैसे कर रहा हूं? थ्रू लॉजिक गेट्स. ओके, क्योंकि मैंने अभी लॉजिक गेट्स पढ़ा इसलिए थ्रू लॉजिक गेट्स. और मैं क्या इंप्लीमेंट कर रहा हूं? मैं Boolean expression इंप्लीमेंट कर रहा हूं. सी सो द $1 million question is how to get this Boolean expression. Let's work on it. Okay, now all 3 aspects will be complete. I know what is my hardware. My hardware is a logic gate. I know how to implement that hardware. That implementation I do by Boolean expression. Now the big question is, क्योंकि अगर थोड़ा आपने सोचा तो there are 3 levels. Hardware is the lowest level. Boolean expression is the second level. जो मेरा Boolean expression है वो मैं hardware में implement कर रहा हूँ. That is what you see. तो अभी सोचना ये है कि ये Boolean expression मुझे कैसे मिलेगा. तो ये बहुत इंपॉर्टेंट है डिजिटल लॉजिक डिजाइन में. Okay, no doubt मैंने आपका सिलेबस देखा है. And I have done my homework because before I start any lecture I always do my homework. My homework refers to all minute details I go through. So my opinion is that आपका जो स्टडी है डिजिटल लॉजिक का वो थोड़ा रेस्ट्रिक्टेड स्टडी है क्योंकि you are studying digital logic as a part of COE. Actually this is a subject in electronics telecommunication or electronics engineering. Full-fledged 18 month subject called digital logic design. So that you are studying at level just to support your main subject, that is COE. So I'm going to restrict myself. I'm not going to unnecessarily make it very complex. But I'm going to show you all the required details. That is the main part. So now let's go to level 1. That level 1 is how we get Boolean expression. Let's go for it. Observe it. These are some of the rules that you have to remember. इसमें मैं ज़्यादा कुछ बोलूँगा नहीं, that ये आपको याद रखना पड़ेगा. Okay. Possibility बहुत कम है कि ऐसा कुछ क्वेश्चन आए कि this is a Boolean expression and you reduce that Boolean expression. Okay, because just now I said कि you are studying digital logic as a part of COE. And that's the reason very minute level question possibility is less. But I shall show you what is Boolean algebra because this is what I use. Okay, so these rules are basically rules of Boolean algebra. Okay, and these rules are simple basically. Couple of rules we'll go through. You can see. Double complement is value itself. See this carefully. I'm just taking some random rules. I will not go one by one because practically it's not possible also. So double complement of x is equal to x, and that is very simple to prove because suppose my input x is 1, and if I take one complement I get 0, and if I take second complement my 0 will become 1. So x double complement is equal to x. Okay, all these rules we may have to apply at some places. Okay, that's why that rules are being presented. Most important rule that we require frequently is rule number 7. Okay, this particular rule we need at many places. X plus x complement is equal to 1. Okay, x plus x complement is equal to 1. Don't worry, I will map it. I will not just show you the rules, but I will also show you where it is applied. Okay, so that you will understand how these rules are useful. But the rules are simple if you observe carefully. X plus 0 is x, or x plus 1 is 1. Okay, and ये बहुत simple because you know what is plus. Plus का मतलब है और. आपने already Boolean expression देखा है logic gates के. X plus y is your OR gate and x dot y is your AND gate. So this is basically OR gate. तो OR gate का अगर second input 0 है, तो जो first input है वही output पे आएगा. ये है आपका second input OR gate का, which is 0. तो अगर वो 0 है तो 1 0 is 1 and 0 0 is 0. Okay, so these rules are very simple. You can just verify using simple logic gates. But discussion that we have done. Now let's see how we use it. And for that, we'll start the design of the circuit. Okay, we'll apply all this understanding to the design of the circuit. And the one design that we do is called as adder. Okay, now this is important for your exam. You can get a small question carrying 5 marks. Design adder. There are 2 types. One is for half adder and second is for full adder. Let's discuss one by one. Let's design adder. What is adder? Adder is a circuit for adding 2 binary numbers. Okay, listen very carefully what I'm talking. I'll change the color of my pen again. ये मेरा पहला नंबर है देखो 1 1 1 1 ये मेरा फर्स्ट पहला नंबर है ये बाइनरी नंबर है and I want to add this number with another number, let us say 1 0. Okay, let me make it better. 1 0. Okay, 1 0 1 1. Okay, 1 0 1 1. Suppose ये मुझे एडिशन करना है, ये मेरा रिक्वायरमेंट है. तो सोचना ये है कि who is going to do this type of addition in your device? Okay, digital device, let us say. So for doing this particular addition, we need a circuit which is called adder. Okay, so how we design it? Please understand. What we do? We try to design a circuit only to add 2 bits. Okay, see this. And once I understand how I can add 2 bits, and I just have to replicate at every place. Okay, because here also I'll be adding 2 bits, here also I'll be adding 2 bits, and here also I'll be adding 2 bits. So our focus is how to add 2 bits. क्योंकि मुझे एक बार ये समझ में आया तो मुझे सिर्फ replicate करना है यहाँ पे. Okay, I can just replicate the same circuit again and again. So let's see what is the circuit to add 2 bits. Okay, and then I can take it to the next level. For that, what we do, we develop a truth table. Okay, we take some inputs like AD or XY. I already said you can give your own names to the input and output. And because we are talking about adder, there will be 2 outputs. One output is for as sum and second output is for as can. It's very simple because when in decimal addition, when we do, then suppose I want to add 9 plus 4. 9 plus 4, when I add, then 9 plus 4 is equal to 13. Okay, so 3 and 1 is my carry, is that way. Okay, so let's see what is the truth table for this particular adder. This is how our truth table looks like. See, my first input is x, my second input is y, my result is sum, and second result is carry. Okay, let's take the same reference what we are doing here. Okay, observe it. What is 1 plus 1? 1 plus 1 is 0, and 1 carry will be generated here. It's simple binary addition, you already know. Okay, so this particular 0 is my sum, and this particular 1 is my carry. So when I try to add 2 bits, I always get 2 results. One is the sum, and second one is the carry. Okay, that is indicated here. See, carry and sum. And of course, I will have 4 combinations. Okay, those combinations are 0, 0, 0, 1, 1, 0, 1, 1. These are my input combinations. So my input can be 0, both the inputs can be 0, or input can be 0, 1, or 1, 0, or 1, 1. In my case, if you see, my inputs are 1, 1. See, here my inputs are 1, 0. See, okay, so all this we present in a truth table. Now it's very easy to develop this particular truth table. It's a very simple rule. You try to understand what is the rule. Suppose I have 2 inputs, then the number of entries in the truth table will be 2 raised to power n. Please understand. So what is n? N indicates number of inputs. Now if you see, in my case, my number of inputs are 2, x and y, because I want to add 2 bits. So 2 raised to power 2 is equal to 4. So I have 4 entries in the truth table. It's so simple. Okay, I hope up to this there is absolute clarity what I'm talking. Fine. Now, let's try to see how to develop Boolean expression. Again I'm repeating. For those who have forgotten, let me once again remind you what is the methodology. At the base, level 3, we have a hardware using logic gates, that is topic and decision. At level 2, we have a Boolean expression, because from Boolean expression, we design our hardware, that means using logic gates. I have demonstrated it. And big question is that how I should get Boolean expression. For that, we need truth table, observe it. So that is how it is interlinked. ऐसा नहीं है कि truth table बनाने का, उसको बाहर करने का, फिर Boolean expression को बाहर करने का. That is not a method. You should be able to develop the truth table on your own. You should try to develop Boolean expression on your own, and from Boolean expression, you should try to realize your digital hardware. That is the process. So we are in truth table. And what is the truth table that I have defined in logic gate? Truth table is a combination of all inputs and corresponding output. That table is called as truth table. In my case, I am talking about 2-bit adder. Once again, observe. These are the 2 bits I want to add. So I have 2 inputs, x and y. This is my x and this is my y. And I have 2 output. One is the sum and second is the carry. Okay, that is indicated here. Now it's very simple how to generate the truth table. 0 plus 0, sum is 0, carry is 0. 0 plus 1, sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. 1 plus 1, sum is 0, carry is 1. Is it okay? I hope all these particular basic operations you are aware. So I will not spend time in explaining how these calculations are done. It's very straightforward. Okay, now the question is that how we are going to design Boolean expression from this particular truth table. There are 2 methods. Listen very carefully. One method is that if your circuit is small, like my half adder circuit is very small because I have only 4 different rows, or I can say input combinations. So what I will do, I will directly look into the truth table. Okay, I will have a look on the truth table, and I will see, observe and understand very carefully. I will see output, carry and sum. क्योंकि मुझे output के लिए Boolean expression लिखना है. हम लोग कैसे लिखते हैं? Z is equal to something. ऐसे हम लोग नहीं लिखा. So Z is output. So I will focus on output. There are 2 outputs, carry and sum. In the output, I will focus on a term where my output is 1. 1 का मतलब है मेरा output generate होता है, और 0 का मतलब है मेरा output generate नहीं होता है. Just like this, I will wait here for some seconds. Okay. 0 का मतलब है output generate नहीं हुआ है, और 1 का मतलब है output generate हुआ है. मतलब मेरा carry generate कहाँ पे हुआ है? यहाँ पे हुआ है. I will focus on this particular entry. Okay. और मेरा sum कहाँ पे generate हुआ है? 2 जगह पे. यहाँ पे sum generate हुआ है, और यहाँ पे sum generate हुआ है. Okay. So I will focus on that. I will forget 0. Because 0 का मतलब है output generate नहीं हुआ है. मुझे उसमें इंटरेस्ट है. मुझे इंटरेस्ट है output कहाँ पे generate हुआ है. Can I identify? Okay. And then I will try to find out what is the corresponding hardware directly from truth table. ये possible है कि मेरा truth table छोटा है. इसको समझो अच्छे से. Okay. Say for example, my output is 1 when both inputs are 1. Can you see? इसका मतलब है मुझे सिर्फ AND गेट लगेगा, बाकी कुछ नहीं लगेगा. My output is 1 when both inputs are 1. Okay, otherwise it is 0. See, ये किसका characteristic है? ये characteristic AND गेट का है. Output is 1 when both inputs are 1. Otherwise it is 0. See, so this is the typical characteristic of AND gate. ये AND gate का truth table है. अगर आपको recollect हो रहा है तो. Okay, so I will require just one AND gate. मुझे AND gate चाहिए. Carry को handle करने के लिए. Okay, and if you see sum, you will find my output is 1 when both inputs are different. 0 1, output is 1. 1 0, output is 1. And when both inputs are same, my output is 0. See, 0 0, both the inputs are same, output is 0. 1 1, both the inputs are same, output is 0. This is the typical characteristic of XOR. अगर आपको याद है तो. So this sum I can implement using XOR gate. Observe it carefully. So what we do to get the circuit, we identify the gates which match with our output. That is what I was doing for last 2-3 minutes. And we directly write the Boolean expression. So what is the Boolean expression for carry? See this. Carry, I represent it as C. The Boolean expression is XY. Of course, बीच में dot रहेगा. हमेशा अगर लिखना है ऐसा रूल नहीं है. XY का मतलब है बीच में dot है और is and. Okay, it is understood. हमेशा dot लिखना है ऐसा नहीं है. And what is the Boolean expression for sum? Boolean expression for sum is XOR gate. Okay, so how it looks? Observe it carefully. X bar. Okay, bar I am representing by dash. Observe it. यहाँ पे लिखा है X dash का मतलब है X complement means logic 0. Okay, so this is X bar. Observe it. ये X bar. Let me map it. Okay, this is Y. Observe it. Okay, this is X. Okay, no bar. See this. And this is Y bar because Y is 0. So what is my Boolean expression? X bar Y and X Y bar. And this is typically XOR gate. And once I get Boolean expression, I can directly draw my digital logic circuit like this. Observe it. This I said XOR and. See, this is the final implementation of half adder. Okay, let me talk about it. Observe it. X dash Y, X Y dash. मैंने यहाँ लिखा है. देखो, X dash Y, X Y dash. Okay. और दूसरा क्या एक्सप्रेशन है मेरा? C equal to XY. Observe it. ये जो है ये पहला एक्सप्रेशन है और ये दूसरा एक्सप्रेशन है. वो I have written. See. Okay, and this I can realize in 2 ways. That's why I have written 2 ways for half adder, implementation of half adder. Okay, what are the 2 ways? One way is using basic gates. I already told you and or and not. These gates are called as basic gates. Okay, so don't use anything. Use only basic gates. See how. x okay is my one of the input, y bar is my second input. Observe it carefully. Okay, अगर आपको थोड़ा उसको और प्रिसाइज करना है तो आप क्या कर सकते हो? I just save some time here. यहाँ पे लिख रहा हूँ. What you can do is that you can call input as y this way. Okay, this is my input y and you can show it as not gate this way. Observe it. Okay, this is my not gate. और not gate के बाहर जो आउटपुट आएगा that particular output will be y dash. Okay, ये जो y dash है वो यहाँ पे डायरेक्ट दिखा है. See, it is okay. क्योंकि अभी सबको पता है कि कॉम्प्लीमेंट का मतलब है नॉट गेट. Okay, and dash is a complement. मैंने यहाँ पे बहुत क्लियर लिखा है क्या see. Dash मतलब है x complement, y dash मतलब है y complement. मतलब लॉजिक 0. Okay, so if you have time limit तो आप डायरेक्टली दिखा सकते हो यहाँ पे y bar. Okay, this is perfectly alright. If you have time है, you can show this way. Y given to the not gate and what to get is the y bar. Okay, so this is one term x dot y. X dot y bar. दूसरा टर्म है x bar y. See, x bar y. वो मैंने दिया है AND गेट को. मैंने ऑलरेडी बताया कि कुछ अगर लिखा नहीं है तो इसका मतलब है डॉट ऑपरेटर मतलब AND गेट. And both these terms you are ORing. So output of AND is equal to input to OR. You can see. And what you get is the sum. Carry का तो straightforward है. उसमें कोई ऑप्शन नहीं है. Directly you are using AND gate. See, x and y are the input and carry is the output. Okay, this is one way. लेकिन उसको अगर थोड़ा सिंपलीफाई करना है तो आप क्या कर सकते हो? I already said that this is basically XOR. ये जो पूरा एक्सप्रेशन है वो XOR गेट है. Okay, so this you can represent directly as XOR gate. See. Okay, and you can reduce these three gates by single gate. Observe, ये जो पूरा है, this you have replaced by single gate. That gate is XOR gate. Okay, and of course we can't do anything about AND gate. ये तो basic gate है. So that part is as it is. If you see the second realization, and what you get is this realization. Okay, both realizations are correct. लेकिन उसका हर एक का अपना प्लस एंड माइनस है. वो आपको समझना है. ऐसा नहीं है कि एक अच्छा है और दूसरा बुरा है. हर एक का अपना प्लस माइनस है. Because I always say that the thing is perfect. Okay, so let me comment in 2 minutes. Okay, कि what is the plus and what is the minus. इसका प्लस पॉइंट ये है कि you are realizing this entire hardware using only basic gates and or not. These three gates are basic gates. Okay, and availability of basic gate is better than availability of other gates. Okay, इसका ड्रॉबैक ये है कि इसमें नंबर ऑफ गेट्स इंक्रीज होते हैं. You can see यहाँ पे नंबर ऑफ गेट्स रिड्यूस होते हैं. You require only 2 gates. लेकिन इसका प्रॉब्लम ये है कि availability of gates XOR gate easily available होगा. Possibility is 50-50. Okay, because XOR gate is very specific. But and or not, these gates are very general. They are always available. So that's why I will not say one is better and other is bad. Both are correct. It depends what gates are available, what hardware is available, in which application you are using, how many other circuits are there in that application. So these are some thought before we select one or two. If you have any queries, you are free to ask. Our half hour discussion is completed. So I'm waiting for your queries.
सर वो ट्रुथ टेबल और इसके बाद जो आपने एक्सप्रेशन लिखा है वो कुछ मतलब मैच नहीं हो रहा सर.
एक मिनट मैं पीछे जाता हूँ. पीछे यहाँ पे गया मैं. एक मिनट. हाँ, यहाँ पे कौन सा एक्सप्रेशन? एक्सप्रेशन
तो मतलब एस सम इक्वल टू जो आपने लिखा है वो और सम के आगे तो हमें एंड गेट चाहिए था ना, कोई इतने सारे एक्स कॉम्प्लीमेंट वाई वगैरह कैसे.
नहीं, सम के आगे एंड गेट नहीं, कैरी के आगे एंड गेट है. सी
तो हां कोई
कैरी
यहाँ पे एक्स और
कैरी के आगे एंड गेट है बराबर.
यस
और सम के आगे एंड गेट नहीं आएगा क्योंकि सम के यहाँ पे दो आउटपुट जनरेट हुए. सी
हां वो एक्स और
तो एक्सओर गेट है. तो वो ऐसे ही रखा है. सी कैरी के आगे एंड गेट है. ये मेरा कैरी है और ये मेरा एंड गेट है. और ये मेरा कैरी है और ये मेरा एंड गेट है. और सम के लिए मैंने एक्सओर गेट यूज किया. सी और ये एक्सओर गेट मैं ऐसे नहीं रियलाइज कर सकता हूं. मैं अभी आपको एक्सप्लेन कर रहा हूं. एंड ऑल गेट. तो इट इज ऑल्टरनेटिव.
सर और जब हम सम का मतलब सम कैलकुलेट कर रहे हैं तो जो पिछला सम ऑपरेशन हुआ उससे जो कैरी जनरेट हुआ वो भी कंसीडर करना चाहिए ना.
नहीं हो रहा है. दैट आप जो रिफर कर रहे हो एकदम वैलिड पॉइंट है. इसलिए हम लोग आगे दूसरा सर्किट डिस्कस करेंगे जिस पर फुल एरर. तो इसका लिमिटेशन है. इनफैक्ट मैं वो क्वेश्चन पूछने वाला था बट एनीवे यू पॉइंटेड इट आउट. इसका लिमिटेशन क्या है? दैट वाज माय नेक्स्ट क्वेश्चन. वी आर गोइंग फॉर इट. आपका पॉइंट बराबर है.
ओके
या एनी अदर क्वेरी चेक इट आउट. एंड लाइक आई सेड दिस ऑल पीपीटी आई विल शेयरिंग एज पीडीएफ. तो आप मतलब अगर ऐसा कुछ बहुत ज्यादा इंपॉर्टेंट है तो ये सब नोट करो. ये सब कुछ एनीवे आई विल शेयरिंग और नोट्स में भी ये सब अच्छे से दिया हुआ है. आपका जो वीडियो पे आपको मिलेगा मॉड्यूल 1 का रीड है. Okay, so check it out. If any queries are there, I'm ready to answer your queries. Let's take a breathing time here for maybe a couple of minutes. I will try to resolve your queries. Anyway, we have completed almost 50% of our discussion. थोड़ा हम लोग आज पूरा डिले हो गए. मेरे को थोड़ा अपना आपका एजेंडा पूरा नहीं होगा ऐसा लग रहा है क्योंकि बहुत कुछ आगे है. ठीक है. Can I go ahead? If you are ready, then please type YTS. Sorry, come to know you are there. You are ready, and there are no queries. Let's follow that protocol. Yeah, that's very nice. ठीक है, fine, very nice. Okay, ठीक है. Let's go ahead. अभी थोड़ा अपना डिस्कशन कॉम्प्लेक्स होने वाला है तो आपको थोड़ा अच्छे से ध्यान देना है. ओके, मैं थोड़ा क्विकली गो थ्रू करता हूं सो दैट अगर कोई पॉइंट्स स्किप हुआ होगा आपको समझ में नहीं आया होगा तो आपको वो समझ में आएगा. ठीक है. तो वापस एक रिव्यू करके आगे चलते हैं. तो आई एम गोइंग टू हाफ एडर 1 सेकंड. इनफैक्ट दिस पॉइंट important understanding is that we always design digital circuit in 3 phases. In phase 1, we think about the hardware. That hardware is a logic gate. A very fundamental digital hardware is a logic gate. आपको वो सब कुछ याद रखना पड़ेगा. स्टार्टिंग का जो मैंने सब बताया. सेकंड लेवल इज बूलियन एक्सप्रेशन. क्योंकि सोचना यह है कि मैं हार्डवेयर बनाऊंगा कैसे. उसका थॉट प्रोसेस क्या है? उसका थॉट प्रोसेस है बूलियन एक्सप्रेशन. फ्रॉम बूलियन एक्सप्रेशन वी इंप्लीमेंट हार्डवेयर. जो मैंने आपको बताया वापस वो स्लाइड बता रहा हूं सो दैट इफ यू हैव लॉस्ट यू विल रिकल. ये जो हम लोग ने ये डिस्कस किया था. अब ये कहां से आया बूलियन एक्सप्रेशन पता नहीं है. मेरा फोकस यहां पे क्या है कि बूलियन एक्सप्रेशन मुझे पता है मुझे हार्डवेयर बनाने को आना चाहिए. ये हम लोग ने यहां पे देखा. ओके, सो दिस इज लेवल 3 एंड दिस इज लेवल 2. नाउ द $1 million question is that ये बूलियन एक्सप्रेशन मुझे मिलेगा कैसे. For that we started a design of adder circuit. Okay, we started practical application called adder. For that I said मुझे दो नंबर्स ऐड करने हैं. Let's assume my first number is 1111 and second number is 1011. तो मैं ये नंबर्स ऐड कैसे करूंगा? What is the circuit in my digital device? Answer is अगर मुझे बाइनरी नंबर्स ऐड करने हैं then I will look at a big number in a small part and that part is only LSB. अगर आपने ध्यान से देखा तो मैंने जो सेपरेट किया है वो है LSB. और LSB क्या है मैंने आपको लास्ट सेशन में सब पढ़ाया था. Boolean convergence. What is the LSB? What is the MSB? What is the weight? WEIGHT. Why it is called as LSB? Why it is called as MSB? ये सब कुछ हम लोग ने सेशन 1 में डिस्कस किया था. तो मैंने जो ये सेपरेट आउट किया है वो है LSB. मुझे ये जानना है कि मैं ये दो बिट्स को ऐड कैसे करूंगा. अगर मुझे ये पता चला तो सेम हार्डवेयर में हर जगह रेप्लिकेट करूंगा. ओके, हम लोग कॉम्प्लेक्स सिस्टम हम लोग कैसे बनाते हैं? कॉम्प्लेक्स सिस्टम हम लोग एप्लीकेशन से बनाते हैं. ऐसा नहीं है कॉम्प्लेक्स सिस्टम में हर चीजें अलग अलग है. ऐसा नहीं है. There is only one fundamental hardware which is replicated. So I focus on addition of 2 bits. How I'm going to add 2 bits? That circuit is called adder. Okay. For that, I designed a truth table. Okay. उसमें मैंने आपको एक रूल बताया. Rule is how to design a truth table. Truth table will have all the inputs and it will have all the outputs. I will have 2 inputs. मेरे पास 2 bits हैं जो मुझे ऐड करने हैं और ऐड करने के बाद मुझे 2 आउटपुट मिलेंगे. एक सम और दूसरा कैरी. How many entries are there in truth table? उसका सिंपल फॉर्मूला है 2:n. n is number of inputs. Inputs कितने हैं? 2. x and y. 2 bits ऐड करने हैं. What is 2 to the power 2? 4. तो मेरे पास 4 कॉम्बिनेशन रहेंगे. ओके, और वो कॉम्बिनेशन तो सिंपल है कि वो है 0 0 0 1 1 0 1 1. ओके, मुझे पता नहीं है आपने होमवर्क में कितना किया है. लास्ट टाइम मैंने काफी कुछ होमवर्क दिया था. लेकिन अगर आपने देखा तो यह है डेसिमल 0, यह है डेसिमल 1, यह है डेसिमल 2 और यह है डेसिमल 3. इतना सिंपल है. आप कन्वर्ट करके देखो. 0 0 कन्वर्टेड टू डेसिमल इज 0, 0 1 कन्वर्टेड टू डेसिमल इज 1, बाइनरी टू डेसिमल कन्वर्टेड. 1 0 कन्वर्टेड टू डेसिमल इज 2, 1 1 कन्वर्टेड टू डेसिमल इज 3, 0 1 2 3 ये मेरे इनपुट्स रहेंगे. इट इज सो सिंपल. ओके, लेकिन बाइनरी में वो डेसिमल में याद करने को इजी है इसलिए मैंने आपको बताया. इनपुट्स है बाइनरी में. तो मैंने ट्रुथ टेबल बनाया And after that I told how to design Boolean expression. One way is that आप अच्छे से ट्रुथ टेबल देखो, आपका आउटपुट देखो और आउटपुट कहां पे जनरेट हुआ है वो आइडेंटिफाई करो. जैसा कैरी जनरेट हुआ है एक जगह पे, ओके, बाकी सब जगह पे 0 है. Try to model it in terms of gate directly. That gate is an AND gate because AND gate generates result 1 when both inputs are 1, otherwise it is 0. तो यहाँ पे मुझे AND gate लगेगा. Sum कहाँ पे जनरेट हुआ है वो मैंने आइडेंटिफाई किया, okay, and that characteristic is a XOR gate and then I implement it. ये सब मैंने आपको possibility सब बताया. Now the question is what is the limitation of half adder? See, suppose I want to add two n bit numbers, n is an integer, okay, जैसे कि ये मेरे दो numbers है, 4 bit numbers है मेरे. See, this is my 4 bit number and this is my another 4 bit number. इनको मुझे add करना है, okay. Then can I use half adder? Okay, ये दूसरा example है. I want to add 8 bit number with another 8 bit number, okay. Can I use previous adder? Basically that is 1 bit adder, okay, क्योंकि हम लोगों ने 1 bit लिया है. The answer is no. Okay, why no? Because this particular adder is called as half adder. Observe this word very carefully. Why it is called as half adder? The reason is when you add, okay, when you add, you are only considering two inputs. You are not considering carry which is generated from the previous addition. Observe what I am talking. देखो, what you are trying to add are only these two inputs. See, okay, these two inputs. लेकिन ये क्या है उसका क्या करेंगे आप? ये तो जनरेट हुआ है पहले एडिशन से, लेकिन वो कंसीडर नहीं होगा. So the problem with this particular design is that this particular design can add only 2 bits. This design cannot consider the carry which is the third bit generated from previous addition. क्योंकि अगर यही सर्किट में सब जगह रेप्लिकेट किया तो प्रॉब्लम ये होगा कि ये जो कैरी जनरेट हो रहा है वो कंसीडर नहीं होगा. Such circuit is called half adder. Why half adder? Because it only considers sum. It do not consider carry. उसके लिए वो वर्ड है half. देखो, वो कंसीडर क्या करता है? वो सिर्फ sum जनरेट करता है, वो carry कंसीडर नहीं करता है. That's why such circuit is called half adder. This circuit is not so useful. अगर मुझे practical adder बनाना है तो multi bit adder. For that, what I need is a circuit, and that circuit is called full adder. Have a look. Okay, now let's see what is the full adder. Now what is a full adder? Full adder is a circuit which can add 3 bits. Observe it. What are the 3 bits? Let's see. Can you see? You will find a truth table where now I have 3 inputs. Okay, what are 3 inputs? Let's understand here. This is my 1, 1, 1, 1. I want to add 1, 1, 1, 1 with some random number. Let us say 1, 0, 1, 1. Okay, and this type of addition I want to perform. Then 1 plus 1 is 0, and 1 carry will be generated here. Do you agree? Now this carry we are considering as third input. Such type of adder is called full adder. So basically, if I want to map, then this particular carry is my C, this particular one is my B, and this particular one is my A. Such type of adder is called full adder. And full adder is the basic adder we use in design of digital system. कोई भी अगर addition करना है उसका circuit है full adder. Okay. Now let's see how it looks carefully. I already said that when you have 3 inputs, what are the 3 inputs? A and B are the inputs which are actual bits, and C is a carry which is coming from previous addition. I have clearly shown here for clarity. Practical example mapper is a truth table. So ABC are my inputs. Number of inputs are 3. So number of entries in the truth table is 2 raised to power 3. That means 8. So I have 8 entries in the truth table. This is slightly complex than half adder. क्योंकि half adder में 4 entries है, full adder में double entries हो गए, 8 entries. Okay. Now what are the entries? Simple, 0 to 7. उसका binary आपको लिखना है. See, 8 entries है, 0, 1, 2, 3, 4, 5, 6, 7. See, 0, 1, 2, 3, 4, 5, 6, 7. उसका binary. इतना simple है. और that is a combination, very simple. And now let's understand the table carefully. 0 plus 0 is 0. 0 plus 0 is 0. No carry, no sum. 0 plus 0 is 0. 0 plus 1 is 1. No carry. 0 plus 1 is 1. 1 plus 0 is 1. No carry. 0 plus 1 is 1. 1 plus 1, sum is 0, carry is 1. 1 plus 0 is 1. 1 plus 0, sum is 1, no carry. 1 plus 0 is 1. 1 plus 1, sum is 0, carry is 1. 1 plus 1, sum is 0, carry generated, see. And 0 plus 0, sum 0, no carry. Previous carry remains as it is 1. 1 plus 1, 0, carry generated, see. And 0 plus 1 is 1. So simple truth table we have completed. अभी यहाँ पे प्रॉब्लम ये है कि how to generate a Boolean expression, okay? यदि अगर आप अच्छे से सुन रहे हो सेशन को, we have completed almost close to 2 hours, so I know that level of saturation starts coming now. But if you are listening to our session very carefully, you will agree that I said एक बार truth table बन गया तो there are 2 ways we can generate Boolean expression. One is directly from the truth table if it is small, but that methodology is not going to work here क्योंकि ये थोड़ा complicated है. यहाँ पे हम लोग डायरेक्टली नहीं बना सकते क्योंकि आपको डायरेक्ट गेट नहीं मिलेगा. उसका 2 रीजन है. एक रीजन तो है कि हम लोग 3 इनपुट्स कंसीडर कर रहे हैं और अपना जो गेट्स है वो हम लोग नॉर्मली डिफाइन करते हैं बाय 2 इनपुट. हम लोग ने स्टार्टिंग में जो टेबल बनाया था तो ये थोड़ा डिफिकल्ट टास्क है. So the question is how we will get Boolean expression for sum and for carry. That is a big question. Can you tell me what is your opinion? I just want to know out of curiosity. I think my question is very clear. How you will get Boolean expression for sum and carry? That is my question. Can you tell me how?
सर ट्रुथ टेबल में हम देखेंगे कॉलम्स कैरी का है, उसमें एंड और का कुछ ऐसा दिख रहा है और सब में एक्स और एक्स नॉट दिख रहा है, तो अकॉर्डिंगली फिर सोच सकते हैं क्या करें.
But dear, that methodology is difficult and that methodology is not reliable. Okay, so your thought process is correct because you are just following what I thought. Okay, so there is nothing wrong in your thought process. But this is not the perfect technique. Anybody else? But anyway, your contribution is good. Anybody?
जैसे और एक थॉट प्रोसेस है, जब हम 2 बिट कंसीडर कर रहे थे तब हम बेसिकली एक बिट देखते थे. अगर एक एंड गेट में एक बिट 1 है तो आंसर 0 आएगा, और दोनों बिट 1 है तो आंसर 1 आता है. अब यहाँ पे 3 बिट्स है तो विल कंसीडर ओनली 2 बिट्स. दैट इफ 2 बिट्स आर 1 देन द आंसर विल बी 1. फॉर रेस्ट ऑल द ऑप्शंस इट विल बी 0. तो फिर वैसे भी सोच सकते हैं.
ओके, ठीक है. मतलब बेसिकली यू जस्ट वांट टू एक्सटेंड दैट आइडिया. दैट इज योर आंसर. जो हम लोग ने हार्डवेयर में किया वो आप एक्सटेंड कर रहे हो. ठीक है. एनीबडी एल्स हु कैन कंट्रीब्यूट? Anyway, now let's go ahead. No problem because I will teach. Problem is that what one of your friends is telling is correct because he just following what I taught and his thought process is correct. What we do in simple truth table, I will just try to do it in complex truth table piecewise. But the problem is that just imagine if I have 4 inputs, then there will be 16 entries in the truth table. If I have 5 inputs, then there will be 32 entries in the truth table. So method 1 may not be suitable. So I want a little general method to find Boolean expression from the truth table, and that particular method is called K-map. Please understand. Observe it. Can you see this word? Okay, you can see a simple blue color text and that is called as K-map. Okay, this is the crux of our discussion for today's session. K is the name of the scientist. It is called as Carnot map. And all history and all that you can see after session is complete. Maybe before we meet Saturday, what is Carnot map? Carnot is the name of the scientist who has invented this methodology. Okay, just a quick history. K-map is the gold standard if you want to get Boolean expression from the truth table. आपके पास अगर truth table है और आपको अगर ये Boolean expression मिलना है तो gold standard is K-map. Okay, let's study K-map. Your concentration is required. I will say more than 100%. Okay, let's see what is K-map. K-map is basically a graphical technique. Okay, ध्यान से समझो क्योंकि एक बार मैंने आपको एक K-map explain किया तो उसके बाद आप उसको easily explain कर सकते हो. ठीक है, तो try to understand. What is the K-map? This is how our K-map looks. Okay, don't worry, मैंने अभी बताया नहीं है. What you see is the truth table of our full adult. मुझे रेफरेंस के लिए चाहिए. It is the same truth table जो मैंने आपको यहाँ पे पढ़ाया, डिस्कस किया, वही है यहाँ पे. Okay. What is the K-map? This particular graph is called as the K-map. ठीक है, ये आपको सब ड्रॉ करना होता है, नोटबुक पे सॉल्व करना होता है. जो कैसे करते हैं मैं आपको पढ़ा रहा हूँ, उसे अच्छे से समझो. Basically, this particular K-map we are drawing for 3 inputs. Do you agree? See, because I have 3 inputs. हम लोग K-map हमेशा इनपुट के ऊपर ड्रॉ करते हैं to get the output. आपको समझा? हमेशा हम लोग K-map इनपुट के ऊपर ड्रॉ करते हैं to get the output, which is the Boolean expression. क्योंकि आपने यहाँ पे देखा तो ये मेरा Boolean expression है जो K-map से मिलता है. ये मेरा Boolean expression है जो K-map से मिलता है और वो मुझे चाहिए यहाँ पे. क्योंकि वो मेथड अदरवाइज बहुत डिफिकल्ट है अगर हम लोग कन्वर्जेशन कॉम्बिनेशन से किया तो और वो गलत भी हो सकता है. So, how I approach the K-map? How we draw K-map? Understand carefully. We always draw K-map in the form of a small table. आपको यहाँ पे छोटा सा टेबल दिख रहा होगा. Okay, this table is basically a K-map. Okay, one K-map I'm drawing for sum and other K-map I'm drawing for carry. Is it okay? I repeat it. One K-map we are drawing for sum and other K-map we are drawing for carry. Is it okay? मतलब ये आपको समझा कि कितने K-map ड्रॉ करोगे, जितने आउटपुट्स है, मेरे पास आउटपुट्स दो है, कैरी और सम, तो मैं दो K-map ड्रॉ करूंगा. ओके, और K-map ड्रॉ इसके ऊपर करूंगा, इनपुट के ऊपर करूंगा. ओके, आई थिंक नाउ द पॉइंट इज क्लियर. हाउ टू ड्रॉ? लेट्स सी. नॉर्मली व्हाट वी डू, वी टेक रो. आप ये जो देख रहे हो ये रो जो मैं पॉइंट कर रहा हूं, ओके, दिस पर्टिकुलर रो और दिस पर्टिकुलर रो वी टेक एज एमएसबी. कैन यू सी व्हाट इज एमएसबी? इसका एमएसबी है x. ओके, तो हम लोग रो लेते हैं. देखो ये है रो, वो है x. ये है रो, वो है x. ओके, और इसमें जो कॉलम्स है, ऑब्जर्व इट, ये जो कॉलम्स है, तो कॉलम्स में रिमेनिंग टू इनपुट, बाकी के दो इनपुट्स क्या है, y एंड z. कैन यू सी? यू कैन सी हियर y एंड z. तो ये है मेरे कॉलम्स. सी कैसे? लेट मी एक्सप्लेन. I said x is MSB, which is my row, and y and z are remaining two bits, which are my columns. Okay, let's clarify. X can take two values. What are the two values of x? 0 and 1. Observe it. So मेरे ये दो rows हैं. X can take two values. What is the one value of x? Either 0, and what is the other value of x? 1. Okay, and because I'm taking y z, there are 4 combinations. Y z का combinations क्या है? 4 combinations है. Y z के क्या combinations है? आप यहाँ पे देख सकते हो. X can take two values, either 0 या फिर 1. एक मिनट. See, either x can take this value 0, or x can take another value that is 1. ठीक है? और y z values क्या ले सकते हैं? Y z ये values ले सकते हैं. See, 0 0 0 1 1 0 1 1. Okay, see, same values are there. 0 0 0 1 1 0 1 1. ठीक है, तो these values are written here. 0 0 0 1 1 1 1 0. Okay, now थोड़ा आपको ध्यान में रखना है. अगर आपने अच्छे से केयरफुली देखा तो आपको ये समझ में आएगा कि 0 0 0 1 उसके बाद मैंने 1 1 लिखा है. सीरियस, ये मिस्टेक नहीं है, ये टेक्निक है. ओके, वी ऑलवेज राइट 0 0 0 1 1 1 एंड 1 0. उसका रीजन ये है कि हम लोग जब ये लिखते हैं yz द कॉलम्स, ओके, तो वी फॉलो वन कोड व्हिच इज कॉल्ड एज ग्रे कोड, GREY. एक टेक्निक है कॉल्ड एज ग्रे कोड. तो ग्रे कोड में जो सीक्वेंस है वो है 0 0 0 1 1 1 1 0. इसलिए हम लोग उसको चेंज करते हैं. ओके, अब वो ग्रे कोड यूज करते हैं K-map में, वो रीजंस है उसमें हम लोग नहीं जाएंगे क्योंकि आपको उसकी जरूरत नहीं है. ओके, इसलिए मैंने आपको बोला अगर आपको थोड़ा टाइम है, थोड़ा इंटरेस्ट है तो आप थोड़ा लिटरेचर पढ़ो K-map के बारे में, उसमें आपको ग्रे कोड के बारे में लिखा हुआ मिलेगा. ओके, तो हम लोग यहाँ पे K-map के ऊपर R&D नहीं कर रहे, हम लोग K-map यूज कर रहे हैं, तो विल फोकस देयर ओनली. लेकिन आपको ध्यान में रखना है कि हम लोग जब ये लिखते हैं तभी हम लोग सीक्वेंस में नहीं लिखते हैं 0 0 0 1 1 0 1 1. एक जगह पे वो सीक्वेंस चेंज होता है, सीक्वेंस जाता है 0 0 0 1 1 1 1 0. और उसका रीजन अगर किसी ने आपको पूछा तो उसका रीजन है K-map यूज टेक्निक कॉल्ड ग्रे कोड. ओके, बाइनरी कोड यूज नहीं करता है, वो ग्रे कोड यूज करता है. और ग्रे कोड क्या है वो आपको पता नहीं है, इस लेवल पे भी नहीं है. ओके, आई थिंक दिस इज वेरी क्लियर. तो आपको ये फॉर्मेट बनाना है और वो स्टैंडर्ड फॉर्मेट है, मतलब आप हमेशा ऐसा ही फॉर्मेट बनाओगे 3 इनपुट के लिए. नाउ क्वेश्चन इज दैट व्हाट आई गेट. ओके, इतना सब कॉम्प्लेक्सिटी करने के बाद व्हाट आई गेट, लेट्स टॉक अबाउट इट. इफ यू सी वेरी केयरफुली देन व्हाट आई गेट इज सेल, CELL. दिस इज कॉल्ड एज अ सेल. एवरी स्क्वायर इज कॉल्ड एज अ सेल. दिस इज अ सेल, दिस इज अ सेल, दिस इज अ सेल, दिस इज अ सेल. ऑल दीस आर सेल्स. जो ग्रे आपको दिख रहा है उसको सेल बोलते हैं. पॉइंट इज दैट ये मेरा MSB है और ये मेरे रिमेनिंग टू बिट्स है. सो 0 0 0 एड्रेस ऑफ दिस पर्टिकुलर सेल इज 0. मैं यहाँ पे 0 लिखूंगा. 0 0 1 address of this particular cell is 1. 0 1 1 address of this cell is 3. Okay. 0 1 0 address of this particular cell is 2. Last time हमने कन्वर्जन सीखा है बाइनरी टू डेसिमल. 1 0 0 address of this particular cell is 4. 1 0 1 address of this particular cell is 5. 1 1 1 address of this particular cell is 7. 1 1 0 address of this particular cell is 6. Okay. ठीक है. जब आप बनाओगे तो आपको ये पेंसिल और कलर कॉम्बिनेशन वगैरह सब लिख के बैठना पड़ेगा. ऐसा सब अच्छे से कलरफुल बनाना होता है. मैं हमेशा बोलता हूं कलर आप जब K-map ड्रॉ करोगे तो आप K-map ड्रॉ करोगे पूरी पेंसिल से वो डार्क दिखेगा. आपके जो लिखने का जो चीज है 0 1 x का वैल्यू और 0 0 0 1 1 1 0 y z का वैल्यू वो भी पूरी से लिखो. अंदर का जो एड्रेस है जो मैंने आपको लिख के बताया 0 1 3 2 4 5 7 6, ये जो एड्रेस है वो आप ब्लैक पेन से लिखो या ब्लू पेन से लिखो. और उसके बाद जो भी काम करना है वो ब्लैक पेन से करो. सो दैट वे ऑल आइडेंटिटीज विल बी विजिबल कि K-map में क्या आपने दिखाया है. ओके, लेट्स गो अहेड. अभी इसके ऊपर हम लोग को काम करना है. नाउ व्हाट वी डू, वी विल फोकस ऑन सम. हम सम के ऊपर सबसे पहले फोकस करेंगे. ओके, वी विल टेक सम. नाउ आइडेंटिफाई व्हेन सम इज बीइंग जनरेटेड. जैसे मैंने आपको पहले बताया था जहां पे 1 है वहां पे आउटपुट सम जनरेट होता है. तो यहां पे सम जनरेट हुआ है, करेक्ट. तो वो इसका एड्रेस क्या है 0 0 1. कैन यू सी 0 0 1 0 0 1 मतलब 1. ओके, तो यहां पे मैंने 1 लिखा. सी 0 0 1 यहां पे ये 1 लिखा. कैन यू सी K-map में. ओके, कंटिन्यू. ये हम लोग ने K-map में लिखे थे. यहां पे 1 जनरेट हुआ है. व्हाट इज द कॉम्बिनेशन 0 1 0. 0 1 0 का मतलब है 2. सी 2 के यहां पे मैंने 1 लिखा. 0 1 0 तो यहां पे 1 लिखा. ये लिख गया K-map में. यहां पे 1 जनरेट हुआ है. लेट्स टेक दिस वन. उसका कॉम्बिनेशन है 1 0 0. 1 0 0 इज 4. तो यहां पे मैंने 1 लिखा. सी. ओके, एंड लास्ट इज दिस वन. इट इज जनरेटेड व्हेन इनपुट इज 1 1 1. तो 1 1 1 इज 7. तो ये जो 1 है ये यहां पे लिखा. ओके, तो ऑल आउटपुट्स आई हैव टेकन इनटू द K-map. ठीक है, एंड नाउ आई विल जनरेट बूलियन एक्सप्रेशन. हियर आई विल राइट दैट बूलियन एक्सप्रेशन डायरेक्टली. उसका रीजन मैं आगे बताऊंगा. ओके, डायरेक्टली का मतलब है फ्रॉम K-map आई विल राइट द बूलियन एक्सप्रेशन. ऑब्जर्व इट केयरफुली. ऐसे टेक दिस वन. This one indicate x bar, x का वैल्यू है 0 मतलब x bar, y bar z, x bar y bar z, see x bar y bar z. Okay, तो हम लोग ने ये लिया. Take this one. For this one value of x is 0, so x bar y z bar, x bar y z bar, see x bar y z bar. Okay, then we have taken this one. Now take this one. For this one, value of x is 1, so there is no bar, and value of y and z is 0, so there is a bar. X, y bar, z bar. See, x, y bar, z bar. And now you take this one. Okay, for this one, x is again 1, and y z is also 1, so x, y, z. Observe it, x, y, z. This is a Boolean expression for sum. Now, if you are good listeners, because we are reaching almost 2 hours and 15 minutes, a long journey, and a lot of things we have discussed about digital hardware. So, if you are आप ये बोलोगे ये तो मैं ट्रुथ टेबल से लिख सकता हूँ, उसमें केमैप बनाने की क्या जरूरत है, ये तो परफेक्टली वैलिड क्वेश्चन है, ये आपको समझ में आया तो इसका मतलब आपका ध्यान है। ये जो मैंने लिखा, ये तो मैं डायरेक्टली यहाँ से लिख सकता हूँ, ये 1 है तो ये है x बार y बार z। सी, तो आपने ये 1 यहाँ पे मैप करके यहाँ पे लिखा है, ओके? So that is not the case. Okay, that is not the case. And now that I'm going to talk to you, okay, in Cali. The problem is that when we mapped sum onto the K-map, then we cannot further minimize our Boolean expression. Why we use K-map? We use K-map to get minimized Boolean expression. जितना छोटा हो सकता है, उतना छोटा मेरा Boolean expression होना चाहिए। उसके लिए हम लोग K-map यूज करते हैं। क्योंकि आपको थोड़ा अगर आज का सेशन समझ में आया होगा तो आप एग्री करोगे कि Boolean expression के ऊपर मैं हार्डवेयर ड्रॉ करता हूँ, तो मेरा Boolean expression जितना छोटा होगा उतना मेरा हार्डवेयर रिक्वायरमेंट कम हो जाएगा। तो मेरा फोकस Boolean expression लिखना नहीं है, मेरा फोकस है छोटे से छोटा Boolean expression लिखना है, जिसमें ज्यादा redundancy नहीं हो। That we do using the K-map. How? Now you will see when I talk about the Cali. Okay, let's go for it. Now let's do this activity for Cali. Okay, so this is the K-map for Cali. What we do? Again, we write those addresses. वापस addresses नहीं लिखूंगा क्योंकि already वो लिखा है वही रहेगा. This is 0, this is 1, this is 3, this is 2, this is 4, this is 5, this is 6, this is 7. Okay, मैं directly map करूंगा carry bits को. Let's do it. If you see carry, you will find my carry is generated at this position. Okay, वो combination क्या है? 0 1 1. 0 1 1 मतलब 3. 0 1 1. ये 1 मैंने लिखा है, ठीक है? This one, ठीक है. Next carry generated here. It is 1 0 1. 1 0 1 मतलब 5. 5 मतलब this position. Okay, तो वहाँ पे carry लेके गया. Next carry generated at 6 1 1 0. 6 मतलब here. Okay, तो यहाँ पे मैंने carry लिखा 6. And next carry generated at 7 1 1 1. 7 मतलब ये position. तो यहाँ पे मैंने 1 लिखा. Okay, now what you can do? Listen very carefully what I'm talking for next 10 15 minutes. Our K-map will be done. Point is, can you see ये जो ones है वो adjacent one है, उसको मैंने group किया. Can you see this? Observe it. Okay, can you see these two ones? इनको मैंने group किया. Blue color का आपको grouping clearly दिख रहा होगा. Okay, ये जो adjacent ones है उसको मैंने group किया. This grouping will reduce my Boolean expression. वो grouping यहाँ पे possible नहीं है, इसके लिए मैंने directly Boolean expression लिखा. उसके बारे में भी बात करता हूँ. Grouping का effect क्या है? आगे टॉपिक. लेकिन ये जो grouping आपको दिखाई दे रहा है blue color में, वो यहाँ पे नहीं हो सकता. हो सकता है आपके application के ऊपर डिपेंड है कि output कहाँ पे generate हो रहा है. तो सब में वो grouping possible नहीं है. Always remember, grouping you can only do in 2-3 ways. One way is adjacent होना चाहिए, vertical या horizontal. ये vertical है उसको मैंने group किया. ये horizontal है उसको मैंने group किया. Diagonal आप group नहीं कर सकते. ये diagonal है. See, this you can group. This you can group. This you can group. You cannot group diagonal. You can group only horizontal and vertical adjacent. मतलब आपका एक बिट यहाँ पे है. So for example, आपका एक बिट यहाँ पे है और दूसरा बिट यहाँ पे, तो group नहीं कर सकते क्योंकि वो adjacent नहीं है. Okay, so one rule is that in K-map you can do grouping of adjacent ones, vertical या horizontal. Diagonal allowed नहीं है. Because of that, यहाँ पे कोई भी grouping नहीं हो सकता. इसके लिए मैंने ये Boolean expression directly लिखा. लेकिन यहाँ पे हो सकता है. See how? Be alert. बहुत last phase है. Now what is happening here? If you see, let's take one group. Okay, 3 groups है. उसमें से एक group लेते हैं. मैं खुद group करता हूँ, आपको समझ में आएगा. मैं उसकी group की बात कर रहा हूँ. Blue color में थोड़ा confusion हो सकता है. तो मैं सबसे पहले group करता हूँ vertical, क्योंकि vertical एक ही है. Okay, तो see, ये अगर मैंने इसको group किया तो देखो क्या होता है. When I group this, you will find that I am moving from top to bottom ऐसे. Okay, ऐसा मैं मूव कर रहा हूँ, vertical movement कर रहा हूँ. और अगर मैं vertical movement कर रहा हूँ तो आपको समझ में आएगा कि मेरा ये चेंज नहीं हो रहा है yz, क्योंकि यहाँ पे मेरा yz 1 1 है और यहाँ पे मेरा yz 1 1 है, क्योंकि मैं यही कॉलम में हूँ. सी, मैं यही कॉलम में हूँ, तो ये कॉलम में मेरा yz 1 1 है. लेकिन x चेंज हो रहा है 0 to 1. सी, when I'm here x is 0 and when I'm here x is 1, and because x is changing, x term will be eliminated. जो term change हो रहा है उसको हम लोग छोड़ देते हैं. तो x will go and only yz will remain. Observe this yz. आपको ये yz दिखाई दे रहा है? It is coming because of this grouping. और पूरा x चला गया, मतलब आपका एक्सप्रेशन छोटा हो गया, मतलब आपका हार्डवेयर छोटा हो गया. There is lots of understanding in digital electronics. Please understand. Okay? अब ये क्यों होता है? ये मैं आपको बाद में बताऊंगा. सब कुछ साथ में नहीं करते हैं, पहले ये कंप्लीट करते हैं. तो अभी हाथ में लिया है grouping. ठीक है? Now let's go vertical group. Okay? Now vertical grouping में if you see very carefully, then this is my one grouping. ये grouping में अगर आपने देखा तो क्या हो रहा है? मेरा x चेंज नहीं हुआ है, क्योंकि यहाँ पे भी x1 है, यहाँ पे भी x1 है. Okay? z भी चेंज नहीं हुआ है, z यहाँ पे 1 है, यहाँ पे भी z1 है. y चेंज हो रहा है, y है 0 और वो हो रहा है 1. तो मैं y एलिमेंट करूंगा. अभी होगी कि x and z. Observe it. और मैंने अगर लास्ट ग्रुप लिया, सी, ये ग्रुप. Okay? If I take last group, then I will again find x is not changing, x is 1. Okay? Y is not changing, y is also 1. What is changing is z from 1 to 0. तो मैं z को छोड़ दूंगा. What is remaining is xy. Observe it. And this is my Boolean expression, which is called minimized Boolean expression. Minimize का मतलब है इससे कम आप नहीं कर सकते. So from this you can design hardware. And that is the reason K-map is important. Because K-map do not give you just Boolean expression. K-map will give you minimized Boolean expression. Boolean expression with minimum redundancy. That guarantee K-map gives. That's why K-map is a very important technique in digital design. हम लोग कोई भी truth table अगर complex है, ज़्यादा entries है, 4 से ज़्यादा normally, we try to solve it using K-map. Okay, check if you have any queries because I'm talking for a long time and now I should give you time to breathe and time to ask your queries. Check it out if you have any queries. I will answer your queries. I'm in chat box. You can also ask by unmute. Check it out. Any query?
सर आपने वो ग्रुपिंग के बाद चेंजेस बताया कि देखो एक्सचेंज हो रहा है, बाय चेंज हो रहा है, वो जो है वापस रिपीट करूं.
हाँ, वो रिपीट करो, ठीक है. Any other query? I hope you are alert and you are listening carefully and you are understanding that is the reason there is no query. Okay? For the positive. हाँ, क्या बोल?
Grouping is one of the advantages of K-mapping, right?
100%. वो grouping is one of the biggest advantage of K-mapping. You identify
Because of grouping advantage, otherwise reason नहीं है कोई भी.
लेकिन see that grouping is the only advantage. ऐसे बोल के हम लोग उसको लाइटली नहीं छोड़ सकते. उसका रीजन मैं आपको बता रहा हूँ. उसका दो तीन रीजन है. उसका सबसे बड़ा एक रीजन ये है कि because of the grouping आपका Boolean expression छोटा होता है और because of that आपका जो हार्डवेयर है वो बहुत छोटा हो जाता है. तो आपका redundancy कम होता है, आपका कॉस्ट कम होता है, आपका साइज कम होता है. That's a great contribution. This is number one. और दूसरा उसका contribution ये है कि there are different ways you can draw K-map. That are the topic. Okay, what I taught is a 3 variable K-map. This is very important for your subject. आप जो सीख रहे हो उसमें 3 variable K-map एक बहुत कॉमन पॉसिबिलिटी है. Looking at the syllabus. ये सब डिजाइन आपको एग्जाम में आ सकता है. But you can also go for 4 variable K-map, 5 variable K-map, 6 variable K-map. Okay, so this is second contribution why K-map is important. And third contribution is that the way I taught कि आप दो-दो के grouping कर सकते हो. Same way you can do grouping of 4 ones. ऐसा भी grouping हो सकता है. 4 ones का भी grouping हो सकता है. Let me talk about it. Okay, and then I will quickly review how this particular x and y changing. इसका मतलब ये है कि let's assume कि यहाँ पे एक 1 है. Unfortunately यहाँ पे 1 नहीं है, लेकिन अगर यहाँ पे 1 है, then you will find there are 4 ones which are adjacent. This is called as a quad, QUAD. And if you group quad, then 2 variables will be eliminated. अगर हम लोग ने 2 का grouping किया तो एक variable चला जाता है. अगर हम लोग ने quad का grouping किया तो 2 variables चले जाएंगे. That is the advantage of K-map. ऐसे आप क्वाड का रूटिंग कर सकते हो, 2 का रूटिंग कर सकते हो, 8 का रूटिंग कर सकते हो. So concept of K-map is little you can say, I will not say complex, I will say lengthy, क्योंकि उसमें काफी possibilities है. That is the answer to your question. I hope I just answered it, whatever query was there. Anyway, anything else? Okay, now if you don't have any query, let me go ahead and let me once again go through this routing. Okay, fine, very nice. So indication that we can go ahead, that's great. In chat box I can see, ठीक है. क्योंकि एक ग्रुपिंग आपको बताता हूँ, तो अगर कुछ नहीं समझ में आ रहा है तो क्लियर हो जाएगा. I said if you take a vertical group, okay, then vertical group में क्या हुआ है कि अगर आपने अच्छे से देखा तो I am moving vertically, तो x is changing from 0 to 1. अगर ये सेल में हूँ मैं और आगे से सेल में जा रहा हूँ, नीचे के सेल में, तो x is changing from 0 to 1. लेकिन दोनों जगह पे yz remains the same. So I will eliminate x because it is changing, and the term that I will get is yz, जो मैंने यहाँ पे पहले हाईलाइट किया था. That way you can do for remaining two groups. Okay, now let's go ahead. अभी सोचना ये है कि ये टर्म एलिमिनेट क्यों होता है, वो भी मैं आपको बताऊंगा और फिर आगे चलते हैं. ओके, ये टर्म एलिमिनेट क्यों होता है, उसके पीछे रीजन है रूल्स ऑफ बूलियन अलजेब्रा, जो मैंने आपको अराउंड 1.5 आवर्स पहले बताया था. ओके, लेट्स अंडरस्टैंड हाउ. आई मीन जस्ट गिव मी सम सेकंड्स. ओके, नाउ लेट्स टेक दिस केस, वर्टिकल का केस. वर्टिकल में क्या हो रहा है, मेरा वैल्यू है x बार yz. ओके, x बार yz, ये मेरा पहला वैल्यू. ओके, दूसरा वैल्यू है x yz, मतलब ये वर्टिकल ग्रुपिंग में दिस इज x बार yz, और दूसरा वैल्यू है, ओके लेट्स गो दिस वे, प्लस दूसरा वैल्यू है x yz, सी x yz, ठीक है. नाउ yz इज कॉमन, सो आई राइट हियर yz. ओके, एंड in bracket I will say x bar, okay, plus x, ठीक है. यहाँ तो straight forward, yz is common, so I say yz, this in bracket x bar plus x. Okay, now let's go back, see the long journey of today's session. Okay, now see, can you see the highlighted rule? I said this is one of the most commonly used rule. I was talking about this and I highlighted it, and that rule is x plus x bar is equal to 1. Observe it, this is one of the Boolean rule. X plus x bar is equal to 1, this is one of the Boolean rule, and because of this rule x plus x bar is equal to 1, if I apply that rule, then what I will get here is 1. See, we are back. So this x plus x bar is 1 and yz into 1 is yz, and finally what I get is the term yz, which we have listed here. See, and same you can do for horizontal grouping. So term is not getting eliminated because I am saying x is changing from 0 to 1, but it is getting eliminated because of Boolean rule and because of Boolean algebra, and that's why we are directly eliminating it. हम लोग को ऐसा manually solve करने की जरूरत नहीं है. Okay, so now what you have is a Boolean expression for s and c. Okay, यहाँ पे थोड़ा writing mistake है, यहाँ पे s लिखा है, आपने शायद नोट किया होगा, ये actually c है. Okay, I'm sorry. Okay, so this is basically for c, क्योंकि this is all the work we have done for carry. Okay, it's basically doing everything back. So this is my s and this is my c, जो मैंने अभी हम लोगों ने डिस्कस किया. अभी आपका होमवर्क ये है, ऑब्जर्व इट. ठीक है, आई होप यू विल एबल टू कंप्लीट द होमवर्क. आपको करना ये है कि आपको इसके लिए हार्डवेयर बनाना है, और हम लोगों को पता है कि ये सबसे मिनिमाइज हार्डवेयर नहीं हो सकता है, क्योंकि मैंने K-map से बनाया है. जो भी K-map से एक्सप्रेशन आता है वो मिनिमाइज होता है. इट इज सिंपल. कैन यू डू इट? हार्डवेयर मतलब मुझे ये चाहिए, ऑब्जर्व इट. ये मैंने आपको पढ़ाया फुल एडर के बारे में, इंप्लीमेंटेशन ऑफ, सॉरी, हाफ एडर का इंप्लीमेंटेशन, ये मुझे चाहिए फुल एडर का. ओके, सच डायग्राम और आई कैन से रियलाइजेशन इंप्लीमेंटेशन आई वांट फॉर फुल एडर. ओके, सच सर्किट आई वांट फॉर फुल एडर. आई थिंक यू विल एबल टू डू इट बिकॉज़ ऑल रिक्वायर्ड बैकग्राउंड हैज बीन टॉट एंड यू विल एबल टू कंप्लीट. सो प्लीज कंप्लीट ऑल दिस. आई विल शेयरिंग अगेन आई एम पुटिंग अ रिमाइंडर. ओके, दूसरा होमवर्क है जिसमें मैं ज्यादा डिस्कस नहीं करूंगा क्योंकि possibly you will be able to do it, that's why. Second homework is you can also consider full adder as a cascade of two half adder. Observe it. ये मेरा है half adder, ये मेरा है दूसरा half adder. Okay, this input is my x and y, which is the input for half adder, x and y. ये है sum and carry. What I'm doing, I'm applying sum as an input to the next half adder. Observe it. Sum I'm applying as an input to next half adder, and ये जो carry generate हो रहा है पहले half adder से, वो मैं apply directly कर रहा हूँ as a second input to second half adder. And what I get is sum and carry, the final. So this way also you can consider your full adder. Two half adder in series is equal to one full adder. Okay, so this also you try to complete the circuit, hardware circuit. मैंने आपको ब्लॉक डायग्राम से दिखाया है. You try to complete in terms of hardware circuit. ऐसे क्वेश्चन आएगा एग्जाम में, let's see, let's try to mark in exam. In exam you get a question like design a full adder. Okay, this is the question for 10 marks completely. So आपका flow एकदम systematic रहेगा. You will be defining what is a full adder, then you will draw the truth table for the full adder, then you will draw K-map, then you will show the Boolean expression, then you will show the final hardware diagram जो मैंने आपको बताया. Okay, ये homework. Second question ऐसे आ सकता है कि design full adder using two half adders. Okay, उसमें आपको K-map बनाने की जरूरत नहीं है, आपको half adder डिजाइन दिखाना पड़ेगा और उसके बाद आपको ऐसा ब्लॉक डायग्राम बनाना है, दो half adder सीरीज में कनेक्ट करके एक full adder, और उसका सर्किट दिखाना पड़ेगा. सर्किट इसे बनाना पड़ेगा. See, ये दोनों कास्केड में दिखाने पड़ेंगे क्योंकि ये एक half adder है. Okay, लेकिन ये अभी कास्केड में दिखाने पड़ेंगे. The way I was talking ब्लॉक डायग्राम. Okay, उसमें अभी मैं ज्यादा डिस्कस नहीं करूंगा because you will be able to do it all required background we have taught or we have discussed. Okay, so this is how it looks. And ये ट्रुथ टेबल है फुल एडर का जो हम लोगों ने अभी डिस्कस किया. ओके, ये थोड़ा आप उससे करने की कोशिश करो. आई थिंक यू विल एबल टू अंडरस्टैंड. एंड आई एम गोइंग अहेड. नाउ लेट्स थिंक अबाउट सम अदर combinational circuit. Okay, because one important discussion we have completed, if you see the syllabus, this all is listed, like combinational logic circuit compared with sequential logic circuit, logic gates, half adder, full adder, K-map, all this you will find, and that we have done. Now let's start the discussion of some other important logic circuit, and one of the logic circuit is called binary decoder circuit. Okay, let's understand what is the decoder. This is also very common when we try to design digital systems. What is the decoder? Let's understand. Decoder is a circuit which will allow you to select one line out of multiple lines in digital system. Okay, let me explain what I mean. This is very important in communication applications. In communication applications में normally क्या होता है कि there will be many telephone lines and you have to connect one telephone line with other line. Out of many, you have to select one. So in that we use a circuit like a decoder circuit. Let's understand how it looks in terms of truth table. Observe it. What decoder circuit will do? Decoder circuit will give you two inputs A and B, and depending on this two input, it will select one of the output. Like if your inputs are 0 0, it will select line 0. If your input is 0 1, it will select line 1. If your input is 1 0, it will select line 2. If your input is 1 1, it will select line 3. Okay, let's see how. Observe it. And you see, I'm using all basic gates. I'm using AND gate. And I'm using NOT gate, and now you will see I'm using a buffer जो मैंने आपको स्टार्टिंग में सिखाया था along with the logic gates. इसके लिए वो बफर की जरूरत पड़ती है for such type of circuits. Okay, now see what is happening. These are my four lines 0 0 0 1 1 0 1 1. ये मेरा चार लाइंस है. Let's assume that these are my four telephone lines. Okay, और उसमें से मुझे एक सिलेक्ट करना है. कैसे करूँगा? I repeat, these are four lines जिसमें कुछ डेटा आता है और मेरा रिक्वायरमेंट ये है कि मुझे एक एक करके सिलेक्ट करना है, मुझे साथ में नहीं चाहिए, मुझे ऐसे चलना है कि इसको सिलेक्ट किया, थोड़ी देर के बाद इसको किया, थोड़ी देर के बाद इसको किया, थोड़ी देर के बाद इसको किया. For that I need a circuit called decoder. Such decoder is called 2 to 4 decoder. Observe it. Why 2 to 4 decoder? Because I have to select input. Observe it, A and B. Okay, which will select 1 out of 4. So this A and B are two select input, SE, LE, CT, and these are my actual input, which are 4. So this is 2 to 4 decoder. Okay, now let's see how it works. उसके लिए हम लोग truth table use करेंगे. Okay, which truth table? This one. Let's take 0 0. We'll take this combination. Okay, we'll try to understand by this combination. I will highlight it. Okay, so let's study A0 and B is 0. Okay, let me change the color once again and we'll understand. Okay, so my A input is 0 and my B input is also 0. Okay, okay. Now we agree that my 0 is applied as input to NOT gate, so this output will become 1 because you know what is a NOT gate, it is called as inverter. And this is the buffer. Buffer का मतलब है जो input है वही output पे लेगा. So this 0 will appear as it is, as a 0. उसमें कोई change नहीं होगा. Same way, this 0 is applied as input because of this NOT gate. This output will become 1. And because of this buffer, this 0 will appear as it is. That is 0. Okay, now observe. You will find this NOT gate is connected as an input to this AND gate. Okay, so input to this particular AND gate is 1. Similarly, this NOT gate is connected as an input to this AND gate. So input to this AND gate is also 1. So both the inputs to this AND gate is 1 1. If you further see, this is also connected to second AND gate. This is 1. This 0 is connected to second AND gate. So this is 0. Now, because one of the input to AND gate is 0, if you remember our start discussion, today's discussion, when one of the input to AND gate is 0, output is 0. So this is disabled. Nothing is going to come. If you see this AND gate, you will find one of the input is 0. See, this 0 is going here. And because one of the input is 0, this AND gate is also disabled. Nothing is going to come out. Similarly, if you see this AND gate, one of the input is 0. See. And because one of the input is 0, this is also disabled. The only AND gate which will be enabled is this one 1 1. And whatever is coming on this particular line will be available here. Okay, if we are getting some data here, that data will be available, and this AND gate will be selected because all control inputs are 1 1. What you see in colored lines is the control, and what you see in black line is the data input, actual information. That's the convention which is visible. And we say 0 0 will select line number 0. See, 0 0 selects line number 0. And this exercise you can do for remaining inputs also. Maybe as a homework you can try. You can see how 0 1 will be enabled, 1 0 will be enabled, and 1 1 will be enabled. This circuit is called decoder. And because you are talking 2 select and 4 input, this is called 2 to 4 decoder. You have many types. The next possibility is 3 to 8 decoder. 3 to 8 decoder. Now what is 3 to 8 decoder? In 3 to 8 decoder, you have 3 select input and you have 8 data input. So depending on 3 select input, one of the data input will be selected. You have 3 to 8 decoder. You also have 4 to 16 decoder. 4 select input, मतलब ये जो है वो select input है, ये अपना select input है, जो नीचे का पार्ट है, और ये जो ऊपर का पार्ट है वो है data. That is how we work on decoder. Okay? मुझे नहीं लगता decoder के ऊपर कोई ऐसा major question आएगा because it is a concept that you have to understand in digital logic. Decoder हम लोग ऐसा independently कभी यूज नहीं करते, हम लोग हमेशा किसी application के साथ में decoder यूज करते हैं. जैसे half adder full adder में हम लोग directly use logic gate. It's application. जैसे decoder is a supplementary circuit. Decoder is not isolated. ऐसा कभी नहीं होता है कि decoder ही सिर्फ है, बाकी कुछ भी नहीं है. ऐसा नहीं होता है. That is the basic understanding of decoder. Possibly you can get a small question. What is a decoder? Or explain 2 to 4 decoder? Or explain 3 to 8 decoder? ऐसा question आ सकता है. But that's how I have explained how we use logic gates. Okay. Let's go ahead because slowly we are moving towards the end of today's session. Maybe in next 15 to 20 minutes. But we will utilize the time because time is a big question when it comes to syllabus. So let's go and see what is one more circuit which is called multiplexer. Okay. Now multiplexer is just the extension of decoder. मतलब आपने यहाँ पे अच्छे से देखा तो यहाँ पे हो क्या रहा है कि आपका जो डेटा है वो डेटा लाइंस है वो सिलेक्ट होगी. ओके, जैसे कि मैंने आपको बताया इन दिस एग्जांपल कि लाइन 0 इज सिलेक्टेड एंड लाइन 2 3 एंड 4 दे आर नॉट सिलेक्टेड. दैट इज व्हाट वी हैव एनालाइज्ड. ओके, लेकिन अभी आगे का सोचना ये है कि ये तो लाइन सिलेक्शन के बारे में हो गया. मतलब 0 लाइन 0 इज सिलेक्टेड एंड लाइन 1 2 3 आर नॉट सिलेक्टेड. दैट वी डू बाय डिकोडर. लेकिन जो डेटा आ रहा है इसमें जो डेटा आ रहा है उसको कैसे हम लोग कैप्चर करेंगे? उसके लिए हम लोग को यहाँ पे कुछ और चाहिए. आपको समझ में आ रहा है? सी वन सेकंड. What is the decoder circuit? Decoder circuit is a circuit which will have multiple inputs. It will have select input, and using select input, we can identify one line out of multiple input lines. That is called decoder. Many to one is called as decoder. 4 out of 4 select one. That is what is decoder. तो ठीक है, मतलब ये लॉजिक एंड ऑल दैट वी हैव अंडरस्टूड. लेकिन उसका आगे का पार्ट क्या है? उसका आगे का पार्ट ये है कि मैंने लाइन 0 को सिलेक्ट किया एंड बाकी 3 लाइंस को डिसेबल किया. ठीक है, लेकिन लाइन 0 में जो डेटा आ रहा है व्हाटएवर इज कमिंग ऑन दिस पर्टिकुलर लाइन, हाउ आई विल गेट इट? क्योंकि आगे को सर्किट होना चाहिए तो मतलब सिर्फ सिलेक्शन तक हो गया. आगे का क्या? हाउ आई विल गेट द डेटा? क्योंकि इसका क्या करूंगा, इसका क्या करूंगा, इसका क्या करूंगा, क्योंकि यहाँ पे मुझे 0 0 0 मिलेगा. तो आई हैव टू फर्दर अप्लाई सम टेक्निक व्हिच इज कॉल्ड मल्टीप्लेक्सर. Okay, so normally what we do, we use this as a combination. Decoder and multiplexer. These are supplementary circuit. See how it looks. Observe it. How to select one of the 4 input lines and pass the information on a single output line. Okay, तो ये हम लोग decoder से करते हैं. This we do using a decoder. जो मैंने आपको बताया. This we do by decoder. लेकिन आगे का जो पार्ट है, this one. This we do using a multiplexer. See how. Can you see what is the difference? It's so simple and very conceptual. मतलब normally people just draw blocks की दो input, एक box निकाला और 4 output निकाले and they say that this is my 2 to 4 decoder. Okay, 2 input है वो select है और 4 जो है वो है आपका selection lines. Okay, और उसके से single output आता है. So that is not the way you should study decoder. Decoder is not a block diagram study. Decoder you study in terms of circuit, combinational circuit. That means logic gate. Next step of decoder is a multiplexer. Now what you see in multiplexer is entire decoder is same. उसमें कोई difference नहीं है. Okay, I have just added a single OR gate and now I have a complete circuit where many to one type of communication is possible. Okay, because this AND gate will be enabled. Here I always get 0 क्योंकि all these particular AND gates are disabled. So I will write here 0. I will write here 0. ये सब कुछ मैंने आपको पढ़ाया आपको. I will write here 0. So this is 0 0 0. Now what is going to happen? Whatever data is coming here, this data can be 1 or this data can be 0. That is going to appear at this particular output because all remaining inputs to OR gate is 0. And मैंने आपको already पढ़ाया OR gate में कि when one of the input to OR gate is 0, output is the last जो remaining input है. ये input अगर 1 है, you will get 1 as the output. ये अगर 0 है, तो you will get 0 as output. And this data will be available on this line. Same way, if you say 0 1 0 1, this data will be available here. Similarly, if you say 1 0, this data will be available here. Similarly, if you say 1 1, this data will be available here. And that circuit is normally called switching. SWITCHING. We normally design switching circuit using decoder and multiplexer. और वो switching क्यों चाहिए? क्योंकि ये communication में ज़्यादा हम यूज करते हैं कि multiple communications are going on. So what we do, we go on switching between all these communication. थोड़े टाइम के लिए इसका लिया, थोड़े टाइम के लिए इसका लिया, थोड़े टाइम के लिए इसका लिया, थोड़े टाइम के लिए इसका लिया. ये common communication link है. The information highway. On that information highway, we can put our information from multiple channels using this circuit, decoder and multiplexer. एक बहुत बड़ा fiber optic cable या coaxial cable यहाँ रहेगा. ये सब स्ट्रेट पेयर cables रहेंगे जो individual channels है. And all these individual channels which are subscribers or clients, we can put it on main information track using this circuit. ओके बहुत मतलब हम लोग थोड़ा डिटेल में गए मतलब माय इंटेंशन इज दैट यू शुड अंडरस्टैंड व्हाट इज डिकोडर एंड व्हाट इज मल्टीप्लेक्सर यू शुड नॉट ओनली स्टडी एक ब्लॉक डायग्राम उसमें 2 इनपुट और 4 ऐसे दिखा है और आउटपुट दिखा है दैट इज नॉट वे यू स्टडी इन टर्म्स ऑफ कॉम्बिनेशनल सर्किट ये मुझे पता है ओके नाउ only small part is remaining from our agenda because when I started at 5:30 I just provided the agenda and many points I have projected and many points we have covered only some discussion is remaining we will roll it over that is not the issue but I will start because at least we will get the that's all okay
सर यहाँ पे और गेट लिखिए ना कि अगर वन इनपुट वन रहेगा तो ही आउटपुट भी वन आते नो मैं करेक्ट बोला हां यस ऑब्वियसली इफ वन इनपुट इज वन तो और गेट का आंसर भी वन आएगा सो यहाँ पे और गेट चालू रहेगा और यहाँ पे एक बार से एक ही लाइन चालू होता है तो जो गेट में से और डेटा आएगा डेटा और गेट में से बनते हैं
एकदम बराबर आपको क्लियर है I was about to ask if you have a query then you can raise your query what is the time I can answer your questions but anyway this very limited I'm happy that you're asking and I love because that is how learning is possible so let me answer your question आप बरोबर बोल रहे हैं इसमें थोड़ा मैं ऐड करूंगा मतलब information is missing that's why आपको ये सोचना है आपका सोचना ऐसा होना चाहिए कि अगर मैंने यहाँ पे 0 0 अप्लाई किया सिलेक्ट इनपुट ओके तो उससे क्या होगा कि ये तीन जो लाइंस है वो डिसेबल हो जाएंगे जो हम लोगों ने पहले एनालिसिस किया और एग्जाम में मस्त एनालिसिस करके कलर से ब्लू ब्लैक पेंसिल से दिखा के दैट वी कैन डू वी हैव टू वी नो एंड वी आर नॉट जस्ट ब्लॉक डायग्राम वी नो द सर्किट सो पॉइंट इज ये अगर मुझे 0 0 है मेरा सिलेक्ट इनपुट एबी सिलेक्ट इनपुट तो ये तीन जो एंड गेट है वो डिसेबल हो जाएंगे तो उनका वन ऑफ द इनपुट 0 जो मैंने आपको पहले बताया तो उसका आउटपुट 0 होगा एंड गेट का अगर एक इनपुट 0 है तो उसका आउटपुट 0 नहीं है ट्रुथ टेबल से ठीक है एनीवे क्या होगा एनीवे ये लाइन मैंने टिक किया है अगर आपको सोचना ऐसा है कि इसका मतलब क्या है कि ये लाइन पे जो भी डेटा आएगा जिसमें डेटा आएगा 0 1 0 1 0 1 ओके वो डेटा यहाँ पे अवेलेबल होगा अगर 0 है तो यहाँ पे 0 आएगा अगर ये 1 है तो यहाँ पे 1 आएगा तो ये एंड गेट जो बाकी दो इनपुट है वो 1 है बिकॉज़ दिस इज 1 1 तो ये जो लाइन है वो लाइन का जो डेटा है वो यहाँ पे आएगा 0 है तो 0 आएगा 1 है तो 1 आएगा एंड बिकॉज़ दिस ऑर गेट उससे क्या होगा कि ऑर गेट के बाकी के जो इनपुट्स है वो 0 है बिकॉज़ ऑफ दैट जो डेटा यहाँ पे आने वाला है सेम डेटा अपीयर ऑन द आउटपुट लाइन मतलब यहाँ पे ओके बिकॉज़ ऑर गेट का फीचर क्या है कि ऑर गेट का अगर एक इनपुट 0 है ओके तो जो दूसरा इनपुट है वो आउटपुट हो रहा है जैसे कि एक जैसे 1 0 एक इनपुट 0 है तो 1 गेट आउटपुट तो 1 0 is 1 सिमिलरली 0 1 एक इनपुट 0 है तो 1 1 is आउटपुट तो एक इनपुट ऑर गेट का 0 है तो दूसरा इनपुट है वो आउटपुट क्या आ रहा है एंड सेम यू कैन डू फॉर रिमेनिंग थिंग मतलब यहाँ पे मैंने 0 1 किया ये सिलेक्ट मैंने 0 1 किया तो ये एंड गेट इनेबल हो जाएगा और ये बाकी के डिसेबल हो जाएंगे 1 3 and 4 डिसेबल तो ये जो डेटा है वो यहाँ पे अवेलेबल होगा एंड थ्रू ऑर गेट इट विल बी अवेलेबल ऑन द अदर लाइन ऐसे सोचना है बाकी बाकी और नहीं एनी अदर वे ओके आई गॉट दिस ओके लेट्स गो अहेड मैं वापस आपको एक रिमाइंडर देता हूं कि प्लीज आप ब्लॉक डायग्राम से मल्टीप्लेक्सर और डिकोडर का पढ़ाई नहीं करें मतलब वो दिखने में टेक्स्ट बुक में बहुत छोटा है जैसे ब्लॉक्स दिखेंगे आपको कि फिर लिखा होगा डिकोडर और नीचे आएगा वो सिलेक्ट लाइन ओके लेफ्ट साइड में आएगा 4 इनपुट और राइट साइड में आएगा 8 आउटपुट और दिस इज डिकोडर दैट इज नॉट रिक्वायर्ड यहां पे आपको समझना है कि सर्किट क्या है और वर्क कैसे होता है बस इतना आपको क्लियर लेना है ओके एनीवे लेट्स गो लेट्स स्टार्ट सीक्वेंशियल सर्किट आई जस्ट वांट टू स्टार्ट बिकॉज़ थोड़ा बोलूंगा लेट इट lot of time almost 3 hours I can say we are talking about combinational logic circuit all the circuits that we are talking starting from logic gates going to half adder going to full adder going to decoder going to multiplexer these are all combinational logic circuit output depends on present state of the input if the present input change output may change second type of digital circuit is called sequential logic circuit and what is sequential logic circuit that already we have defined what are the examples the example which is there in your syllabus is called flip flop observe it you don't have to study shift registers you don't have to study finite state machine okay you have to only focus on flip flop under sequential logic circuit now basically what is a flip flop let me explain anyway we are going to complete our discussion of digital logic design and now we are moving towards computer organization part as we go for more and more lectures you'll find we'll be talking about computer organization one model is the discussion which will start in the next session because sequential logic will be done and immediately we will start with COA part so my point is that we will be talking about memory okay memory like RAM random access memory and everybody knows that in memory we store data in the form of bits zeros and ones question is that how we store data in memory memory में ऐसा क्या है जिससे हम उसको data store कर सकते हैं in the form of bits like kilobits or gigabits group of bits is called as byte okay so that circuit is called flip flop अगर जो memory रहता है उसमें data store करने के लिए जो circuit रहता है उसको बोलते हैं flip flop there are billions of flip flops inside the memory and flip flop is a circuit which stores one bit and that circuit is called sequential logic circuit because there is no memory and in the beginning of combinational logic circuit do not have a memory sequential logic circuit have a memory that circuit is called flip flop let's see what is the characteristic of sequential circuit आपको पता है एक तो मैंने बताया memory and second one is feedback ये दोनों आपने दिखाया लीनिंग में रेड कलर एक लाइन दिखाया which looks like output coming to the input that is called as feedback okay let's see what is the just last 5 minutes or just a start one of the flip flop that we are going to study is called as SR flip flop S stands for ACT R stands for REACT ACT का मतलब है 1 bit 1 और REACT का मतलब है bit 0 क्योंकि हम मेमोरी में क्या स्टोर करते हैं मेमोरी में हम स्टोर करते हैं 1 0 मतलब कॉम्बिनेशन ऑफ 1 0 बिट्स तो 1 कैसे स्टोर करेंगे दैट इज ACT और 0 कैसे स्टोर करेंगे दैट इज REACT so that flip flop is called SR flip flop ACT REACT flip flop that is full form and how it looks like this observe it मुझे आपको सिर्फ ये डायग्राम दिखाना है इसलिए मैं थोड़ा 2-3 मिनट आगे जा रहा हूं because I want to conclude if you see this diagram you will find I am using a NOR gate can you see this is a NOR gate इसका मतलब है combinational circuit यूज कर रहा हूं NOR gate is combinational circuit logic gate is combinational circuit इसका मतलब है sequential circuit में मैं combinational circuit यूज कर रहा हूं and that is what I started in the beginning every sequential circuit use combinational circuit as a design block and it is visible anyway now let's conclude for this session I will not stress you further this is the start point for our next Saturday and we'll complete sequential logic and immediately we will start with the COA part okay so if you have any query then you can ask your query otherwise we will vertical one can you explain vertical one you are referring to this one you're talking about full adder vertical ones well I'm not understanding what vertical ones you are referring can you please tell me I will do it मतलब कहां पे आप रेफर कर रहे हो फुल एडर में कहां पे वर्टिकल वंस ये मैप में
सर जो आपने कैरी के लिए रूटीन क्या वो पूछा गया था
मतलब ये मैप में अच्छा मतलब पहले का फुल एडर का ठीक है वो क्विकली एक मेरे से मैंने वो रिपीट किया था मैंने ठीक है
लास्ट टाइम रिपीट हो गया
मैं बता रहा हूं जस्ट गिव मी 2 मिनट्स एक बार क्विकली दिखा रहा हूं फिर कुछ इंस्ट्रक्शन देना है इससे एक 2 मिनट से फोल्डर को आई नो कि अगेन रेडी कर दिया हम लोग एक क्विकली उसका ये करते हैं अगर किसी को क्वेरी है तो पूछ रहा ये वर्टिकल वंस का मैं जो आपको बता रहा था उसका ये मैंने आपको डिस्कस किया था क्विकली सी व्हेन वी मूव वर्टिकली तो क्या हो रहा है कि x is changing from 0 to 1 and x is getting eliminated okay तो क्यों हो रहा है रीजन इज if you see this one then this is x bar yz x bar yz and if you see this particular one then this is x yz x yz is common so in bracket x bar plus x और मैंने आपको एक रेफरेंस दिखाया था कि boolean rules का x plus x bar और x bar plus x is 1 and because this is 1 what remains is yz इसलिए हम लोग डायरेक्टली लिखते हैं ये कैलकुलेशन में करने की जरूरत नहीं है दैट इज द रेफरेंस anyway now all the instructions then we'll end our session see मैंने जो लास्ट टाइम का ppt था वो pdf में कन्वर्ट करके इमीडिएटली 2 दिन के बाद ऑफिस में दिया था या वर्किंग ऑन इट ऑलमोस्ट हो गया है आपको मिल जाएगा वो ebook मॉड्यूल 1 also ready okay so that all will be getting मेरी तरफ से एकदम क्लियर है मॉड्यूल 1 आज भी मैंने आपको कराया उसका pdf में कन्वर्ट करके वीडियो वाला प्ले ऑफिस दैट also will get okay this is the update and please verify those notes ebook का notes होमवर्क कंप्लीट करो आज भी मैंने आपको एक होमवर्क दिया है try to complete it and that's all बाकी कुछ और क्वेरी है पूछो ये अपडेट है
सर जो कर्ली बेसिस के आपने लिखा है और ऊपर वाली लिखा है डिसाइड करें कौन से को वायर कितना कौन से को डिलीट
हां नहीं उसका रूल सिंपल है उसका रूल ये है कर्ली बेसिस के मतलब आप ये बोल रहे हो
नहीं वो तो सम का टेबल है हां वो या फिर टेबल जो कर्ली बेसिस पर लिखा है और फिर नीचे डिलीट ऊपर
ये वाइज लिखा है यहां पे
हां सर वो तो डिलीट लिखा है पहला उसके बाद जेड उसके बाद जो वायर कर्ली बेसिस हां यस
इस वाई एंड इस वाई
यस
अच्छा नहीं वो इसलिए लिखा है नहीं समझ गया वो इसलिए लिखा है कि ये y जो है ना ये जो y है वो सेकंड टर्म है बराबर तो सेकंड टर्म में आपके पास 2 बिट्स है इसलिए मैंने ग्रुपिंग के लिए उसका कोई सिग्निफिकेंस नहीं, समझ गया, कंफ्यूजन समझ गया, इसके लिए सिग्निफिकेंस है, कोई इसका सिग्निफिकेंस नहीं है, बिल्कुल, ये आपका नहीं भी प्रॉब्लम नहीं है, बिल्कुल, उसका कोई ऐसा मेजर सिग्निफिकेंस नहीं है, ये मतलब सेकंड टर्म है तो उसका कॉम्बिनेशन कितना होगा, तो वो सब प्रोसेस उसका कोई सिग्निफिकेंस नहीं है, बिल्कुल। वो जो है ना, ये तीन टर्म आपको दिखाई दे रहा है, x y z, ये x, ये y और ये z, उसका कोई सिग्निफिकेंस नहीं है, उसका एक दूसरा प्रोसेस है, मैंने आपके साथ कम्युनिकेट नहीं किया है, फॉरगेट, उसके बिना मैंने जो बताया उसे आप चेक कर सकते हो, बिल्कुल।
Okay.
भाई ड्राइंग के आपने वही दिखाया, फिर चलेगा, x y and z, ये तीन चीजें कहीं बेस में नहीं दिखाई, नो प्रॉब्लम, नथिंग टू इट, क्योंकि मैंने रिफर नहीं किया होगा, आपने क्या किया, एनी अदर वेरी दैट यू हैव। ओके, ठीक है, मैं इन आवर सेशन सिर्फ एक रिक्वेस्ट करूंगा कि अगर पॉसिबल हो सके तो आप चार वेरिएबल का केना एक बार देख लो, मैंने आपको सिखाया वो तीन वेरिएबल का, तीन वेरिएबल का तुक समझने के लिए और कुछ नहीं, ओके। एनीवे, इन आवर सेशन, थैंक यू सो मच फॉर योर टाइम, ऑपरेशन, this session was also good, थोड़ा लैग हो गया, but it was nice, continuing study, the atmosphere, let's continue next week, 5:30, okay, thank you so much and let's end our session, thank you.